Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, we are continuing in the Integrated Math 2 Big Ideas Math textbook for section 6.3. Within triangles, we are looking at bisectors of triangles. Not angle bisect, well, they can be bisectors of triangles in that same way as well, but you'll see a circumcenter, an incenter, a lot of different things like that. We're gonna have some fun. Want to apologize about the 6.2 video. If you got to the end on number 38, it cut short. You probably even hear me a lot of times during the video say, I don't know how much computer room I have and things like that. Well, I ran dry and I didn't even know it. I finished the problem as I was recording and I was like, that ought to do it, guys. And I found out the recording ended. Thankfully, I got through the majority of it. There's a snapshot of it in the description section of that video for the answer to the last question, basically, if you want to see that. And I think I resolved my issue when it came to disk space. Part of it is I do have some PC games on here. I moved them to an external drive, at least some of them, not all of them, but I think I have enough memory now for a 3-hour video if I needed it. I don't know how long this one's going to be. I hope that I don't run into that issue here. And also, apologize for redundancy of attire if that happens. It is now softball season. Green is not my favorite color, but it's our school's color, and we are in season effectively, and it's a little cold being in January. So anyway, let's go ahead and get started with the material. Guys, we are looking within this triangle bit stuff. Hopefully you've been okay on some of the proofs because I don't know if this will have proofs. I'm looking at this first page thing right now and it looks like there's something where through the examples they're referring to the circumcenter stuff and there will be a proof on a page, maybe through the examples. However, in the problem sets, I don't know if there will be proofs, but you know what? That's a part of what geometry is. We prove these theorems. They're all used in that way. They all involve triangles. We're in a chapter of triangles. Totally legit. All right, let's look at what we will learn today. We will use and find the circumcenter of a triangle, use and find the incenter of a triangle. Those are the two big things here. Some core vocabulary on the side: concurrent, point of concurrency, and then circumcenter, incenter. Previously, perpendicular bisector, angle bisector. We saw those before. Let's see what they want to, how they want to define it, and I'll see if I want to reinterpret it for you. Using the circumcenter of a triangle, when 3 or more lines, rays, or segments intersect in the same point, they are called concurrent lines, rays, or segments. The point of intersection of the lines, rays, or segments is called the point of concurrency. So, for example, right here, you see this point of concurrency in this image, and then all of these are concurrent in that way. In a triangle, the 3 perpendicular bisectors are concurrent. The point of concurrency is the circumcenter of the triangle. I didn't skip anything, right? Okay, no. Okay, so let's look at, and I'm sure they're going to tell us about it right here, but let's look at this diagram and what they just said in this last part, or really even before that. See, if I have 2 lines that intersect, of course they will be concurrent because they're like that. But if I draw a third line, it doesn't have to be concurrent with them. It could be like that. But what if it's like this? Now suddenly they're all concurrent, right? So that's what you're seeing here. And what they're telling you, guys, is there is concurrency for the perpendicular bisectors of a triangle. They didn't mention angle bisectors yet, but they are for the perpendicular bisectors of the triangle. So what are perpendicular bisectors of a triangle? They are, I guess from this point, if you will, but no, excuse me, from the midpoints of the sides of the triangle, if you draw a perpendicular line out from them, then they will all meet at the same point, so these blue ones. And that's what they're telling you. Now, we're going to talk about what a circumcenter is in general after this. I'm sure they will give you visuals. If not, I will gladly do it for you. The circumcenter theorem. It says the circumcenter of a triangle is equidistant from the vertices of the triangle. So this point itself, that point of concurrency, where those 3 perpendicular bisectors meet, mind you, where you draw those 3, this point has equal distances to the vertices of the triangle. These 3 red segments here are congruent. These are congruent right here. Pretty nifty stuff. Now, there's a reason why that is as far as the congruency. That's how a circumcenter works when it comes to a triangle. There are a lot of things within a triangle, guys, that if you don't know about it yet, you'll go like, I didn't know that. Like, that's kind of cool, unless you're not really that fascinated by math. But when you hear circumcenter, you might be thinking circumference, and I'm sure they're going to talk about it, but I want to reveal it right now. As we're showing it, I'm going to draw a circle. I'm going to draw a circle from this point. This point will be that center, and I'm going to draw it to any one of these 3 points right here, like that, and take a look. This circumcenter circumscribes that triangle, or the triangle's inscribed within the circle there, but it circumscribes the triangle. All 3 points hit there, which means those 3 red lines, those 3 red segments, are radii. And of course, radii in a circle are congruent. They all go the same distances out. But it just so happens that the point of concurrency is where those 3 perpendicular bisectors meet, which is also pretty nifty. So if PD, PE, and PF are perpendicular bisectors, then PA equals PB equals PC is what you show there. There's a proof, and it looks like it is this one right here. Proof is on the page, and it's right below. I don't know if I'm going to dig too much into, well, you know what? I think it's worth digging into the proof. It's all about congruent triangles and using CPCTC. Actually, no, it's not for this one. You know, I think I'm going to skip this proof, actually. It's kind of I'm going to skip the proof. Let's move forward on how you're going to use that stuff. Are we all already on solving a real-life problem? Okay. Let's do an example through here. 3 snack carts. Let's move this over. 3 snack carts sell frozen yogurt from points A, B, and C outside a city. Each of the 3 carts is the same distance from the frozen yogurt distributor. So you see frozen yogurt here, here, and here, 3 points outside the city, boom, like that. They're the same distance from the distributor being probably the circumcenter then, right? Find the location of the distributor. Okay, now how are you going to find that location? It's best if you draw out perpendicular bisectors from these segments, because we may know that all these 3 are the same distance from that point, but those 3 won't help you find that point. Perpendicular bisectors will. Now, how you would do it, they say use a ruler and protractor. The whole idea for this, of course, is what you'd have to do is actually measure how long this is and take half that distance, get a midpoint. Measure how long this is, take half that distance, get a midpoint. Measure how long this is, take half that distance, get a midpoint. And then they say use a protractor, something that can measure out 90 degrees and make 90-degree lines and draw them out and then find where they intersect. You can also use a compass in this scenario. We did perpendicular bisectors with a compass in section 6.2, but they're actually measuring those out. Wherever they intersect is the circumcenter. And once again, drawing a circle out with this can kind of show you that those 3 points work in that way. Circumcenter. All right, at least if I drew it perfectly. I missed some information over on the side here. Let's see what they say. The prefix circum means around or about, as in circumference, like kind of what I was saying before. Okay, this is an example for us to do. We'll leave it. Okay, the circumcenter P is equidistant from the 3 vertices. Oh, okay, so now they're showing you this, and this is kind of another unique way of showing where circumcenters exist as well. So the circumcenter is equidistant from the 3 vertices, as shown below. The location P depends on the type of triangle. The circle with center P is said to be circumscribed about the triangle. So that's what I was saying before. Circumcenter is the center of the circle that you could draw on the outside, and all 3 vertices of the triangle are on the circle. What I didn't tell you is that the circumcenter is inside the triangle when you have an acute triangle. And an acute triangle is a triangle with all acute angles. Remember, a triangle will always have 2 acute angles, but what is the 3rd angle? Is it acute, right, or obtuse? When they're all acute, circumcenter is inside of it. Has to do with the nature of how the perpendicular bisectors are drawn, and that's what you're looking at with these arrows. These are perpendicular bisectors. Where they intersect is a result of staying inside of them because they all angle inward in that way. When you have a right triangle, however, the perpendicular bisectors work a little differently because the ones for the legs of this right triangle intersect at the hypotenuse just by nature, and then the hypotenuse one starts there and it goes right on there. So in a right triangle, the circumcenter is on the hypotenuse of the triangle. It's on the triangle itself. Now, when you have an obtuse triangle, meaning only one obtuse angle, of course, but an obtuse triangle such as this one, now they actually intersect on the outside. So you have this perpendicular bisector here. You want to draw it both ways, and on the outside and on the outside, because the way they angle out, they have to go meet on the outside there. That doesn't mean the vertices aren't on the circle itself. Right there, nothing like that, but that's just the circumcenter. That's where it is. These distances are still the same distance away from the vertices of the triangle. Those are still equidistant. That does not change. Okay, let's, they talk about compass construction here. Do we want to do this? Yeah, sure, let's do it. Use a compass and straight edge to construct a circle that is circumscribed about triangle ABC. So I'm going to go ahead and play with the compass construction. This kind of is a problem in and of itself. So let's have some fun with it. I want to change the thickness of it. Maybe I can't. Maybe that's the thickness I have to work with. So this might take a minute, but what I'm going to do is I'm I'm going to draw myself some, and this will not be perfect, by the way, guys, mostly because, oh shoot, what was that thickness? 91. Mostly because, things won't hit perfectly. I already just missed. I didn't draw this arc fully enough. But things won't hit perfectly because I'm not drawing this thing at perfect length. See, I'm already missing how this arc is already drawn. This will not be a perfect science, basically. But I'm going to draw perpendicular bisectors like this. Basically, what I do is I extend an arc outward from both sides of this thing, and I draw a line that goes through them. That's a perpendicular bisector of segment AC. I can erase the arcs now that I did that. We'll go ahead and make that perpendicular bisector the blue. And because this looks like an acute triangle, close to a right one, but because it looks like an acute one, then that means that the circumcenter will be inside this triangle. Oh, I have to change this color. Change it to green. All right, let's draw another arc here. I'm going to do the perpendicular bisector for segment AB now. So let's do that one, or at least close enough to it. Sorry if you don't want to spend this time in the lecture on it, but it's kind of an example, if you will, showing this construction. Now let's draw a line through that one. Right here. Now, if this is done right, only 2 of them would technically need to be drawn. Technically, only 2 of them should need to be drawn, which means that should be the circumcenter right there. Because the third one should be concurrent with those ones, right? That's the whole idea. Why draw 3 of them? I guess for the sake of the example, but why draw 3 of them when 2 will do, right? That's the idea. Anyway, so let's draw a third set of arcs here for this BC. So there, and then let's do it right there. Sorry about this. Whee! And let's find where those guys intersect. So if done perfectly, you should see the point of concurrency be there, that all these should be concurrent. If done, yeah, maybe not so, then it won't be right on. See, this isn't right on the button, because my compass construction thing isn't perfect given the computer stuff. But let's pretend it was around there, right? Around there, if I thickened it out, I can say, okay, point of concurrency. Now, what did the point of concurrency give once again? What's the concept? This point is the same distance away. I'm going to erase everything but the point. This point is the same distance away to all 3 vertices. It's a fat version of the point, but this length is equal to this length is equal to that length. All these are the same. That's what we found. That's the idea. And, oh, they have an example down below where they show it. I probably should have just looked at that. I apologize. I totally didn't even see that. So they drew 2 as well. And then they show that point of concurrency, and that's what we get. Okay, guys, let's move forward. Finding the circumcenter of a triangle on a graph. Find the coordinates of the circumcenter here. Now, the general thing, once again, and I think it's an important note that I mentioned on the last one, because they are, because the point of concurrency, because the circumcenter is a point of concurrency of 3 points, you technically only need 2 to find that point of intersection. The third one is not a requirement. You know it will be there. You don't have to draw all 3. The third is just a courtesy, basically. So find 2 of them. So for this one, what do? They find the midpoint of segment AB, and because these are vertical, it's very easy to count. They're both 2 away from here, and 3 away from here or here is the midpoint of BC. And perpendicular to a horizontal line is vertical, perpendicular to vertical is horizontal, and then they intersect right there at 3, 1. So 3, 1 is the circumcenter, which is also on the triangle because this is a right triangle. So I'm going to go kind of the fast route of that. I assume we're going to have to do those for problems as well in the problem set. Okay, let's talk about the in-center, and let's see. I can scroll this thing over to the left, so I'll do that. Looks good. Using the in-center of a triangle. Just as a triangle has 3 perpendicular bisectors, it also has 3 angle bisectors. The angle bisectors of a triangle are also concurrent. So when you draw the angle bisector of angle A, the one that makes these congruent, and of C, and of B, they also intersect at the same exact spot. Not the same as the perpendicular bisectors, mind you. It's not the same spot as that. This is a brand new point. This point called P is now the in-center of your triangle. Really cool that it's concurrent. Triangles are very special in that way. So this is called the in-center of the triangle. The in-center always lies inside the triangle. Now, if you know that a circumcenter circumscribes a triangle, it might make sense that an in-center inscribes a triangle. So what are these perpendicular things right here? Those are not perpendicular bisectors. Clearly, this point F is not the midpoint of A and C. It is the shortest distance from this point P to this segment AC. So what does that actually mean? This is my center of a circle where if I draw it to any of these points, it hits all three. This circle inscribes this triangle. They hit these 3 points here in such a way that, and listen, drawing a circle is not the requirement. Drawing a circle is explaining that all these 3 distances are the same, that this is congruent to this, that these lengths are equal. PD, PE, and PF, found by drawing the angle bisectors and finding their point of concurrency. That's the whole concept. That's what we're doing. So, looks like they're going to do different kinds of examples this time, ones that I expect to see a little more of, probably algebraic and such. In the figure shown, the length of ND is 5x minus 1, and I understand, listen, I understand these drawings can look confusing. They can for me as well, because they're color-coded. That is actually helpful. In the figure shown, ND is 5x minus 1, and NE is 2x plus 11. So here's ND, here's NE. They're going to ask us to find the length of NF and ask us, can NG be equal to 18? Explain your reasoning. Okay, so they're going to explain some of it, and I'll go ahead and elaborate on that as well. What you see here are those perpendicular segments, not perpendicular bisectors, but what you see here are the segments that show the shortest distance from this in-center point, using the in-center, from this in-center point to there. Now, how do I know this is an in-center? They didn't tell us that. Not even this. They didn't tell us that. How do I know? They show that these are angle bisectors, that these are congruent bits. That makes this the in-center. That makes these lengths equal, which means ND and NE have the same length, so you set this equal to that, and that's what they're doing down below. 5x minus 1 equals 2x plus 11. You solve for x, you get 4. To find the length of NF, NF should also be equal in length to ND and NE. So to find the length of NF, we will substitute 4 into either expression for ND or NE. They're the same. Substitute 4 and you get 19. So ND is 19, NE is 19, and NF is 19. Okay. Now part B asks you, can NG be equal to 18? Explain your reasoning. So this length is 19 right here. They're asking if this can be 18, and I'm going to say no, and here's why. They're probably going to explain the same thing, but I'm going to say this way. Notice that this here is a perpendicular segment, which means this can make this thing a right triangle. In a right triangle, the hypotenuse must always be longer than either leg of your right triangle. If this leg is 19, then it's impossible for the hypotenuse to be 18. It must be more than 19. So no, it's not possible for NG to be 18. So let's see what they say. Shortest distance from the perpendicular is length of 19. Okay, well, they said it even faster. That's the shortest distance there. Therefore, anything longer must be longer. So even easier, but right triangle is another talk on that. All right, let's move forward. Here's that drawing of that circle, the inscribed circle in the in-center. That's what they say, circles inscribed. I'm not going to construct this one this time. They show you what they do. Angle bisectors, though, I haven't taught you how to do that. You draw a compass construction from these two, draw some arcs, and find out where, draw a line through those arc intersections, and that's the angle bisector. Draw 2 of them. You don't have to draw 3, but draw any 2 of them, and that should be the point of concurrency. And then, boom, you have an in-center. Okay. If we have to do it later, great. If they talk more about it, we'll make sure to do that as well. Okay, solving a real-life problem. A city wants to place a lamp post on the boulevard shown, so the lamp post is the same distance from all 3 streets. That means the closest distance to the streets is the same. That means we're talking in-center. Should the location of the lamp post be at the circumcenter, or, I just answered it. Circumcenter or in-center of the triangular boulevard? Explain. It should be at the in-center. To be the same distance from all 3 streets, it means the closest distance. So we are talking in-center in this. And that's kind of what they're saying as well. In-center is the equidistance from all sides. It should be the in-center. Doesn't look like they're actually doing any problems with that, but that's it. Draw a sketch to show the location. I don't know. You draw 3 angle bisectors like this, this, and that. And then suddenly, boom, it would be around there. And that means that this distance, and this distance are the same. Lamppost right there. Beautiful. Okay. All right. We're done with that notes part. So let's go ahead and move into the vocabulary and core concept check, and then we'll do the problem set, which does seem longer. There are 50 some odd problems, but maybe they're shorter problems. When 3 or more lines, rays, or segments intersect in the same point, they are called concurrent lines, rays, or segments. Concurrent. Okay, which one doesn't belong? Which triangle doesn't belong with the other 3? Explain your reasoning. The black represents the triangles. So what we see here, I do see 3 acute triangles. Boom, boom, boom. So that's a thought. It could be that these are the same, and then this is the different one. Odd man out. They are showing circumcenters. Sorry, this one they're showing a circumcenter. That's a circumcenter. They're showing circumcenters for all of them. No, they're not. They're showing circumcenters for these 3, and they're showing incenters for these ones. I noticed that because this one shows equidistance to the vertices. That's what a circumcenter does. And this one shows equidistance to the segments here. That's what this one does. I'm going to say there's an argument to be made here, here, and here, because these are acute triangles, and therefore... Well, but see, this isn't a circumcenter. Okay, I'm going to negate this one. I was going to say the first 3 were acute triangles, therefore their circumcenters would be inside the triangles, which is true. While this is an obtuse triangle, that circumcenter's on the outside. But this isn't the circumcenter anyway. It doesn't matter if it's inside or not. That's not the circumcenter. So that's not the relationship they're talking about. I'm going to guess they're showing circumcenters for these 3, and they're showing the incenter for this one. So that's my guess on what they say, which one doesn't belong. Explain my reasoning. The first 3 show circumcenters. And the last one shows an incenter. And that's by showing the congruent marks, not from the perpendicular bisectors, angle bisectors, but rather from the distances to the things that all should be equal in length. The distance to the vertices on the first 3, and then the distance to the triangle sides on the last one. Okay, guys, we're going to move into the problem set now, so get ready. Find the PDF down below if you want to copy down all of these and look at the timestamps for the certain problem sections that you are looking for. Let's rock and roll. Let's go ahead and get started here. We are going to be looking at exercises 3 and 4, where they have the perpendicular bisectors shown in blue. Now, they didn't overlabel it, which means they're not showing perpendicular bisector, perpendicular bisector, right? They're not showing that. So just keep it in mind. They tell you what they are, so we'll go with that. That means that we got to go off that information and say, what do we have here? But find the indicated measure. So on number 3, we do have perpendicular bisectors, and where they are concurrent is the circumcenter. Not the incenter, but the circumcenter, which means these 3 lengths are congruent to each other. They ask you to find the length of BG. BG should be the same length as AG. Therefore, BG is 9. I'm just going to say BG equals AG, which is 9, because they are the same. And that's number 3. See, short and sweet. Number 4, we also have, again, perpendicular bisectors, which means we're looking at a circumcenter. I was going to mention something else about incenters. Oh, the incenter is always inside of the circle. So if you were having a question as to what this one was here, this is definitely a circumcenter here. Okay, so point G is the circumcenter. So the red are the equal distances to the vertices, congruent, or equal in length, whatever. Find the length of GA. GA should be the same length as GC, which is true. They have a lot more information on this than is required. It doesn't look like they have any other problems which they're using them for, which is kind of interesting. They show all this other information, and yet none of the other ones are used. That length is 11, because the length of GC is also 11. Doesn't matter that that's 9 or that's 7 or anything else. Now, we're going to have to do more work on some problems. I can imagine maybe some Pythagorean theorem or something will be used eventually. I kind of hope there is, because that's quite common in these kinds of problems to use, but it doesn't seem like it so far. All right, in exercises 5 and 6, the angle bisectors of triangle XYZ intersect at point P and are shown in red. So this time we're talking about congruent angles here, congruent angles, not marked, but something that we know, which means these are all concurrent at the incenter. Being at the incenter means these perpendicular lengths you're seeing here are all going to be the same length. So find the indicated measure on number 5. We need to find the length of PB. Now, PB is the distance from the incenter to this midpoint. no, not midpoint, excuse me, to this side right here, which should be the same length as PC and PA. PC is marked as 9, so PB equals the length of PC, which is 9. Number 6, find the length of HP. Okay, same thing. We have an in center right here, which means these are all the same length. Boom, boom, and boom. They want the length of HP. We know that the length of PK appears to be 15. You see it marked in blue. 17 appears to be that hypotenuse, if you will. So 15, they're giving you almost too easy of problems. It doesn't look like there's any more work than we need than that. HP is the same length as KP. Kim Possible, which is 15. Okay, it's number 6. All right, let's look at number 7 through 10, where we will find the coordinates of the circumcenter of the triangle with the given vertices. This can only be helpful with a drawing, with a graph. So I'll attach graph paper as well. By the way, you might have noticed, or you might notice, because I just noticed, I think this morning when I had to do something for a recent video, I can't use DocDroid anymore for free. So my new hosting site for links, I think, is through Small PDF or something like that. The thing looks a little longer. I hope that they stay up and don't expire as links. So DocDroid is no longer free to host links for. I apologize for that. All right, I have the point A, which is 2, 6, the point B, which is 8, 6, and C, which is 8, 10. So keeping it easy when it comes to the first problem, because this is a right triangle, but more importantly, you have distances that are, or sides that are horizontal and vertical and all that jazz. That means it's easy to find midpoints and it's easy to go opposite reciprocal slope perpendicular to these. We are trying to find the circumcenter, which means it is important for us to determine the perpendicular bisectors of this triangle, and that's exactly what we're going to look to. So pretty straightforward. I want to find the midpoint, and I'm going to choose, remember, it only takes 2 points, 2 perpendicular bisectors. You don't need all 3, but we can confirm it. The midpoint between A and B is 3 away from either, which is this point right here, and its perpendicular bisector would go straight up and down as a result, so I'll also do that in red. It would look like this. It's basically on the line x equals 5. And then between C and B, this midpoint would be halfway in between, which is 2 away on either direction, so it's going to look like that. And we would draw it kind of like that. So where these two intersect is the point of concurrency, which is right there. It should be on the triangle, which is also the midpoint of segment AC, and I don't need to draw the third thing. Doesn't matter where it draws perpendicularly. The point is, this is the circumcenter right here. Now that actual location is 5, 8. So 5, 8 is the location of the circumcenter for that problem. Okay, number 8. Guess we have to get a graph each time, so let's get that ready. This is pretty uncommon for me to not copy down the problem. I know that I didn't copy down the problem on the other ones, but that's because it was a massive diagram, which I just used on the other side. I guess the main reason I didn't copy down the problem here is because I drew them, but I wanted you to know where the drawing came from. But here we go. Number 8. D will be at, let's see, what quadrant do I need to avoid? D will be at -7, -1. E will be at -1, -1. And F will be at -7, -9. So let's plot them. D is -7, -1. E is at -1, -1. F at -7, -9. Once again, kind of an easier version. Right triangle, all within that vertical or horizontal sphere. Apparently it's giving me a skinny right triangle this time, or skinny side lengths, which is fine. Let's go ahead and find midpoints of the legs of this right triangle. Once again, 1, 2, 3, 8 away from each other, so half that distance is 4 away. Let's do the midpoints first. And then this is 1, 2, 3, 4, 5, 6, 7. So that's also 3 away from both of those. So here I get to draw boom and boom. Those are my perpendicular bisectors for this guy. Once again, they are on the right triangle because this because this is a right triangle. So this will be your circumcenter, your circumcenter exists at the point -4, comma -5. -4, comma -5. Okay. What will be nice about using the graph ones, and this isn't the best kind of one to look at. I'd rather find one that's inside or outside. But the graphs are drawn to scale. So it's not me doing compass construction, maybe messing something up or whatever. The graph axes are drawn to scale. So whatever that thing is 100% accurate. I mean, as far as me plotting them. But it's 100% accurate to those actually being equidistant to the vertices of the triangle. So it's kind of nice. So let's see, that's second quadrant. Okay, it's all second quadrant. So let's go. H is at -10, 7. J is at -6, 3. And K is at -2, 3. Okay, so -10, 7. We're going to go up here. H. J is at -6, 3. -6, 3. And K is at -2, 3. Now, this is not a right triangle. In fact, it's an obtuse triangle. I got to label these other sides here. But it's an obtuse triangle, which means the circumcenter will be outside of the triangle. That's the nature of how these perpendicular bisectors will show up. So get ready for that. It's best that you still find at least the perpendicular bisector of the horizontal one. That seems to be a cleanest go-to. I will get that one halfway in between those right there. And halfway in between any of these, there's calculating midpoints, but because we're doing this on a graph anyway, I showed you this in section 6.2. You can count basically like half this slope. You go down 1, 2, 3, 4, over 1, 2, 3, 4. Well, half of that is down 2 over 2. So this midpoint will be right there. Now, the other part you're going to have to do, though, is you're going to have to get the opposite reciprocal slope. This slope was -4 over 4, which is -1. Well, the opposite reciprocal slope is +1 over 1. So it's going to go that direction. So I'm going to go up 1 over 1, up 1 over 1, like that. I actually have to pay attention to a slope when I do that in drawing this, and that's what I'll do. Remember, the other line is going to be vertical for that perpendicular bisector. Whoops. So I know that while this guy in red, not blue, while this guy in red will be drawn diagonally, like so, I know that I'm going to meet it with this guy here drawing that vertical line. And remember, I'm only drawing 2 of the 3 lines. I could have chosen any of those 2, but point being they should intersect there, and I'll draw it in green. That is your circumcenter. The circumcenter is at -4, 9. It was outside of the triangle because this was an obtuse triangle, hoping for an acute one next. But what does -4, 9 actually reveal? Keep in mind, that means that these 3 distances are all the same. This distance, and this distance, they're all equidistant to that point. This point is equidistant to those 3 vertices, I should say. They're all the same. They're all the same. We all the same. Okay. So there we go. That's number 9. All right. Number 10. Let's see if this, let's see if this is an acute triangle. No idea. Let's see what quadrant we're in. The 4th quadrant. They seem to stick to a quadrant. All right. L is at 3, -6. M is at 5, -3. N is at 8, -6. Okay, here we go. 3, -6. 5, -3. 8, -6. That probably looks acute. I can't tell. I assume it's acute. L, M, and it's a little smaller. So I expect that circumcenter to be inside of the this time. I think that's acute. All right. Once again, probably best that I seek the perpendicular bisector of this line, of this side here. 1, 2, 3, 4, 5. Okay, these are 5 away. So halfway between, or half of 5 is 2.5. So halfway between points L and N is 1, 2, and a half away, like that. I'm still comfortable doing that. It's not like any of these will be any better. This goes, let me make sure the points are good. 3, -6, 5, -3, 2. Yeah, that's fine. Okay. Let's go ahead and do, how about this one? Go down 1, 2, 3, go over 1, 2, 3. So half of 3 is 1.5. So we'll go down 1.5 over 1.5 like that. This will be a little tricky But because the slope is still -1, and I think it's a good thing I'm using this one, because the slope is still -1, maybe I could do all three, then the opposite reciprocal slope is still +1, which means I'm going to hit, like, say, for instance, these points here. Boom, boom, boom. Looks like we know where that circumcenter is going to be right there. Boom, like that. So I'm going to go ahead and just draw that up 1/1 deal. And let's go ahead and make that happen. So this perpendicular bisector for side MN will be like that. Perpendicular bisector for side LN will be, again, between those two, like that. Boom. And it's not hitting at a pretty point, but it is still a point indeed. And it's at halfway marks here. So this one is at 5.5, comma, -5.5. So 5.5, comma, -5.5. That appears to be the circumcenter for number 10. A little bit of a slowdown on those last 4 problems, but, got a graph where we got maybe less graphs now. Okay, number 11. Looks like 11 through 14, we are now talking incenters. So, N is the incenter of triangle ABC. Use the given information to find the indicated measure. So again, angle bisectors with A, B, and C are drawn. This is the incenter. That makes these things equidistant right here. They say ND is 6x minus 2 and NE is 3x plus 7. ND and NE being distances to the sides, which are the same. So, with that in mind, we are going to find the length of NF, which should be the same as the other two. So we got to solve for x first. So ND should equal NE, or we should set these two equal to each other. 6x minus 2 equals 3x plus 7. Let's solve for x. I'm going to subtract 3x from both sides, add 2 to both sides, and divide both sides by 3. That's not the solution. We do have to find the length of NF. NF should equal either of these same lengths. So let's do NE on the bottom. And let's go ahead and use that expression, substitute 3 for x. 3 times 3 plus 7, which is 9 plus 7, or 16. The length of NF, just like the other two, is 16. That is number 11. Number 12, same thing, in center. We have equal lengths here, here, here. NG is one of our lengths at x plus 3, and H is another one. Find NJ, same kind of problem. So NG equals x plus 3, and H equals 2x minus 3. They are same distances apart from the from the incenter to the triangle stuff. So NG equals NH. We're going to set x plus 3 equal to 2x minus 3. Let's solve for x. I'm going to subtract x over and add 3 over. X equals 6. Okay, we got to find NJ. It should be the same length as both of those other ones. So NJ is going to be the same length as NG, which is 6 plus 3, which is 9. So all of those have a length of 9, including NJ. Yes, indeed. Yes, indeed. Let's kind of draw arrows to those guys here. That one and that one. So I'm leading the information. All right, that's number... Oh, I didn't move the thing over, but that was number 12. Okay, number 13. Let's see if they challenge us more. I have no idea. They seem to be pretty basic on the first set before, so we'll see. NK and NL find NM. Yeah, no change. We're just working this thing out, so pretty basic stuff. Besides me copying down the problems, it's just the work that we have solving for x and plugging it in. Really, the practice isn't the algebra, right? The practice is knowing what's being requested and knowing how to use the information that you have. And so hopefully you're starting to make sense of the things a little bit, especially when you think of them with circles. These are the same length as each other, so we get set 2x minus 2 equal to negative x plus 10. All this being said, guys, I'm going to add x. I am still expecting some form of working these out a little bit, having a little more difficult of problems. I do expect something like that to happen. A little Pythagorean theorem here and there wouldn't hurt. Anyway, x equals 4. Let's do it with nk. Nm is the same as nk. I got 2 times 4 minus 2. 8 minus 2 being 6. So there's the length of nm. Number 14. Can't really fit it on this page cleanly. I did mention incenters are always inside the circle. I mean, that only makes sense because they're always drawn from the angle bisectors. So those angle bisectors are always inside the circle and wouldn't ever intersect on the outside for any reason. No, yeah, they wouldn't. Number 14, I have NQ is 2x. So I'm going to use that equation when I solve for x after. Assuming this is the same kind of problem. To find NS, NQ, NR, and NS, are those equal distances here? Great. So we're going to say NQ equals NR. Or that is to say 2x equals 3x minus 2. I'm going to subtract 2x from both sides to get x, add 2 to both sides to get 2. X equals 2. Woohoo! So NQ and S is the same as NQ, which is 2 times 2, which is not 2, which is 4. I'm done with number 14. So pretty straightforward problems, no trickery even in the algebra on 11 through 14. Now 15 is a different question entirely. It's not within that section bit, but it is about incenters? No. It's about a circumcenter. P is the circumcenter of triangle XYZ. Use the given information to find PZ. Okay, now we're cooking with something. And here's what I'm going to do. This time I am going to copy this diagram over because I want to enlarge it. They do have some information on these ones that I'd love to label for us. So for this one here, they do say the length of PX is 3x plus 2. PX, so 3x plus 2. The length of PY is 4x minus 8. Where's PY? Right here. 4x minus 8. And they're asking us to find PZ. Okay, so let's keep these things in mind. Number one, they're talking about circumcenter, which means it's where the perpendicular bisectors intersect at that point of concurrency right here. Okay, so the blue ones, and there would be a third blue one, but it's at P, so it doesn't really matter. But when you talk about perpendicular bisectors, P also is a midpoint of here. So if this is 3x plus 2, this is also 3x plus 2. That's really something to keep in mind there, right? Both of those being 3x plus 2. Okay, that's number one. Number two is this. What I'm imagining here. A also serves as a midpoint. And if A serves as a midpoint, then you're talking about these two guys being congruent to each other as well. And with this thing being a right triangle the way it is, this verticality, you're looking at this right here essentially being an isosceles triangle. An altitude to the vertex of a triangle that bisects this thing only can exist in a right isosceles triangle, which means these can be the same length. I'm sure there are other ways I could have described that much better. But the bottom line is, you know, essentially, if I drew like a rectangle here as well, because here's a rectangle, these would be the same diagonals because these are the same lengths, right? And these are the same lengths. So there are a lot of ways we can prove that, you know, we can use HL, congruency, and all that kind of stuff. Anyway, these are the same, excuse me, side angle side, but these are the same length here. What am I getting at? PX equals PY. PX equals PY. Which means we set those equal to each other to solve for x. 3x plus 2 equals 4x minus 8. Subtract 3x from both sides, add 8 to both sides. X is not 8, but 10. X is 10. Okay. Now that solves for x. We got to solve for the length of PZ. Now PZ is the same length as PX because they are equal, right? This is a midpoint. It bisects these. These are equal. So 3 times 10 plus 2. We're going to use that same exact expression, which I guess is the same length as PY, but not really. Don't really care as much. 32. 32. That should be the answer there. Okay, that is number 15. Not even a third of the way done as far as problem sets. And you know that they just get more rambunctious as you go along. So making okay time still. Number 16, P is the circumcenter of triangle XYZ. Use the give. So same kind of question, but a different question. And this one's on the outside. We'll see what we can do with that information. Oh, you know how else? Time out. You know how else I could have said this information? I went to this triangle stuff. You know what deceived me, honestly, was it being on the right triangle itself. You know, if this was in red, it would have helped because that's in red. Remember, these are distances from the circumcenter to the vertices. That would have been a better explanation. It's just, it's hard to see, but circumcenter, this distance is the same as that distance is the same as that distance. An even better way of talking about it. But the point remains that all of these things work to talk about, right? They all relate. It's cool how much interconnectivity, I know maybe it doesn't seem that way to you. It's really cool how much interconnectivity there is in math to say there's more than one way to go about how to talk about this. It's all interconnected. All right, PX is where? Right here. By the way, these are the ones that are going to be equal lengths. So I'm going to mark those right now. But PX is 4x plus 3. PZ is 6x minus 11. Okay, much easier to talk about right here. You can clearly see when it comes to perpendicular bisectors, all that are right there. And here's the circumcenter. You can tell here we're clearly talking about those lengths. So, wow, this is going to be a lot shorter to do as a problem when it comes to saying how it works out. They probably should have started with this one. PX equals PZ, so 4x plus 3 equals 6x minus 11. I guess I should have been the smarter person to say that those are still those lengths. Like, shut up and do the math, Mr. Robinson. I know. I got to find a way to entertain myself, please. X is 7. When we work that out, we get X is 7. Now, PY is going to be the same length as any of these ones here, right? So, PY equals, sure, PX. I can see it on the screen still. That's 4x plus 3. Oh, I'm sorry. We have to substitute 7. 4 times 7 plus 3. 4 times 7 is 28. 28 plus 3 is 31. So there is PY. And all of them. They're all 31. Okay, numbers 17 to 20. We'll draw a triangle of the given type, find the circumcenter, then construct the circumscribed circle. Okay, when I was doing the notes, I kind of regret it now. When I was doing the notes, I did compass construction at the time. And I don't know if they want us to use compass construction or a ruler and a protractor. I'm legit curious. I don't actually know. But number 17, they want a right triangle to do what? Find the circumcenter and then construct the circle. Okay, in a right triangle, I don't want to get too huge. Otherwise, you're not going to be able to notice anything. Oh, boy. Because this isn't about me. It's about you. So I'm thinking that it says construction. I'm going to go back to the previous things and see what example thing they do this off of. Is it the compass like I did before? Or is it the one when they talked about a ruler before? Give me 1 second. I assume it's the compass construction, not the protractor. So I'm going to go with that. All right, well, then we'll do that together. Grab your compasses, folks. 17 through 20. We got some work to do. Now I regret doing this earlier. You know what? This is going to be too big of a triangle. Now I regret doing this earlier for the notes. I didn't know we were going to do this together later. Well, here it is. And none of these are going to be perfect, and this is going to take a while because I don't have... It won't take a while if you know what you're doing and you're not on a computer and you're on paper. It shouldn't take that long at all. It should be really fast. But what I'm going to do is draw myself, and you know what? I think I can do 2 arcs for one set of something, meaning this arc that I draw can serve... Oh, no, that would be too short for the other side. Never mind. I didn't draw it wide enough. Forget anything that I'm saying. But right now, I'm going to be finding the perpendicular bisector for this segment. It's clearly not perfectly constructed, but please go with it. Should be close enough to what I need for the purpose of the problem. And then I will estimate it. Keep in mind, where should the circumcenter be? It should end up being on the triangle because it is a right triangle. Remember, you only need to draw 2 of these sets of things, not all 3. Now let's widen this arc here because I'm going to do one for the bottom. Yeah, that should be wide enough. Yes. So draw one over here, keep it the same width, and draw one over here. You know what part of the problem is besides the technology? Well, it's technology related, is my triangle's just too thick. I can't guarantee I'm going right on a point when I do that. You know what I mean? So going like that. You know what? This one wasn't bad. So when I draw it through, I'm drawing the line through those arcs that I intersected, if that makes any sense. So I'm doing it about right there. That's going to be close enough. Okay, so look at this. This wasn't bad because, whoops, that point of concurrency pretty much appears to be on the triangle. It's right there. So boom. Now, here's what they ask you to do after. They ask you to construct the circumscribed circle. Here's where I believe that, yes, they do want you to use a compass because what you're going to do is plot your pivot here on the circumcenter, and then increase or decrease whatever the width of your compass to one of the vertices of your circle, any one of them. Apparently, this isn't going to be perfect for me, so I'll do the best I can because I can't go exact widths. So I'm just going to go like that. That's the best that I can make my thing. And you do it around there, and it should circumscribe the triangle. Should. Again, mine can't perfectly because I can't do exact widths there. That's kind of the rub of using this technology like that. So it should end up kind of looking like that when all said and done. Circumcenter on the triangle with 2 perpendicular bisectors drawn, right? And then drawing a circle around by increasing the width to that because all those are the same distance and you just can draw it around there. So that's number 17 for a right triangle. Okay, let's go to number 18. Let's just reduce this a little bit. There we go. Let's go to number 18. Let's do an obtuse triangle. Now remember, this is kind of open-ended as far as I can make up my own triangle, and that's exactly what I'm doing. This time I'm going to thin out my triangle a little more, and I'm going to try and make it bigger. Let's go obtuse out here. I think I should be able to fit things this way. And keep in mind, when it comes to circumcenter, it is... I think I have a triangle tool that I can make a triangle out of just a lot faster. When it comes to circumcenter, I only do need 2 perpendicular bisectors. So I'm going to go ahead and maybe just do these outer ones right here. Because if I draw a single arc for both of those outer parts, I think that'll just be the fastest bit. So if I draw one like this, let's do a little bit bigger. Again, I mentioned this in my previous video, I believe. The wider that you make it, the wider that you make your arc, the more room for error that you can have in your stuff. Actually, I'm just going to draw a massive circle for the first one. Just ignore that for a moment. But what I'm going to do is basically find where these arcs intersect for this end and the other end. So for this end, I'm going to draw a line through those 2 arcs. And for this end, I'm going to draw a line through those 2 arcs like that. So even though there's a massive blue circle, what I'm going to do is make a line that goes through this guy, like that. It's going to go pretty far down, and a line that goes through, this is a pretty obtuse triangle, and a line that goes through this guy like that. It's actually probably going to end up looking pretty good. We'll see how good, oh shoot, this circle's going to be huge though. I can shrink the whole triangle afterward, but this should be my circumcenter now. It won't be on the triangle, clearly it'll be outside the triangle. There's the circumcenter. Okay, there it is. So let's delete those other circles. I technically also don't even need these other little bisector guys anymore. But there's that circumcenter. So let's just do this. Let's get rid of those. Let's group this all together as one thing. And let's shrink. Ooh, that moved its piece a little bit. That's okay. And let's shrink this triangle a little bit more because I got to draw a circle. The point is the circle should now be hitting those three vertices, kinda. If the technology allows it. See, you can't shrink it perfectly. That's actually not bad. So we'll do that. That's not bad. Look at that. There's my circle hitting those. That's not bad. Considering how things moved around when I locked it in place. By the way, this was the obtuse. Oh, I'm on 18. I'm sorry. This is the obtuse triangle. And check that out. Ain't math something? All right. Now I hope you're not lost on how I'm doing these. Here's the thing. I hope your teacher kind of taught you how to use a compass and draw perpendicular bisectors. But that's what I'm doing. I'm drawing 2 perpendicular bisectors. I'm finding where they intersect. Now the next one is acute isosceles. That is very specific, which means I do kind of got to use a tool for that. What's interesting is when they say draw it of the given type, I could draw an isosceles triangle by making a perpendicular bisector off of one segment, meaning using compass construction. I'm guessing you're just going to have to make sure that it's just as perfect as can be when you're actually drawing yours. Just draw 2 things of the same length. I'm going to do it this way. But they want acute isosceles, which means I can't go out that way. I have to. This one kind of looks isosceles as well. It was obtuse, though. So this will be an example of acute isosceles. All of these are less than 90 degrees. The circumcenter will be inside of here. So let's do this kind of same thing as before. I'm going to go to this top point. I'm going to kind of just draw just a bigger arc in general. I think if I widen it out. Sorry, give me 1 second. All right, there we go. I'm going to kind of just draw a bigger arc in general to cover 2 different spots. Like that. That's fine. And then on opposite vertices here, I'm going to draw the connecting point to those guys there. So one's going to connect out here and connect right there. And I'm going to draw a line through that. And then for this guy over here, one's going to connect with the big circle right, oh boy, right there and and there. Oh my goodness. This is really tough to do with this tool, guys, because you can only see so much of my screen. So I get to draw a line through this. That's a thick line. I get to draw a line through this and that. And I get to draw a line through this and that. Now where these intersect, that is terrible. That is not even close to being correct. What happened on the drawing? The circumcenter, if this is isosceles, the circumcenter should be met, because, right, this is a perpendicular bisector, right? This should go right there. These should all intersect right in the middle. That was terribly constructed. Oh, I'm sorry. I intersected in the wrong spot here. There we go. There we go. That's a lot better. I don't know. I just saw a point of intersection. I didn't realize that was a triangle. That's significantly improved. My bad. Glad I could call myself out on that. Yeah, I was like, geez, man, Mr. Robinson, you don't know what you're doing. I was going to start from scratch there. All right, there's my circumcenter. Okay, so I got a circumcenter. Let's delete anything that's not the triangle or the circumcenter. So all the arcs, all the perpendicular bisectors. Now let's go to the compass. Oh, I deleted my compass. Let's go to the compass. Need a new one. Have to grab it from the top. Let's go to our compass. Let's widen it out to any one of the vertices, and let's draw a circle around it. This is going to be I was thinking of what is the name of the shape when a circle circumscribes a triangle? I don't know. I wanted to say pentagram, but that's something different. Okay, so this should look like that, and you know what? I could probably find a better. See, look, it kind of didn't hit at the right spot. I can't trust this pivot that I'm going on because it seems to move when I move this. So let's see if that works better. That looks a little better. There we go. Okay, I like that one more. That's the acute isosceles one. Okay. All right, the last one is the equilateral triangle. Now, this should just be right in that middle. So it's almost going to be like the acute isosceles. That was nearly it. Now, I don't know how to make an equilateral triangle with my stuff as much as I... Oh, you know what I can do? Somehow I can find measures of my degrees here. Oh, you know what? I can. I have a tool for it. Okay, here it is. I was going to say there's somewhere where I can actually see my angles. Show height interior angle. See, so right there. Okay, that one's equilateral on this guy. So we know that. Perfect. Okay. So that's equilateral. Let's thin it out. Now, listen, this is going to be very much like the last problem we just had. I mean, you know, there's really not much of a difference. Just pick any of these two and go at it. I need a compass, though. But I need to show you it. So acute isosceles, same-ish as before. Let's start on a point. That didn't really get me on that point, but that's okay. Let's start on a point, and let's do a couple arcs. I'm going to do a perpendicular bisector of the bottom this time. Bottom this time. This is not going to be very precise. It should be. It should be the most perfect kind. Okay, so there's one. Let's just draw its perpendicular bisector now. Kind of moved over a hair. Remember, I'm drawing it through those arc vertices. Okay, there's one. Let's do one from the top. Let's erase the other one, though. And let's continue it a little bit more. I'm getting a phone call. Let me see if I need to take this. Oh, no, it's not. It just says my phone's charged. Okay, and then let's draw where those intersect here. Boom, boom. Okay, and then let's draw that one. Unless you guys are learning construction stuff, you're probably not listening to this section. Or maybe it's ASMR. All right, and this is your, there we go. This is your circumcenter right there. Now, I didn't draw the third set to confirm that, but... Oh, on the last problem... Oh, no, I didn't. I was going to say on the last problem, did I draw 3 perpendicular bisectors? I was able to make the third one because of the... It was just an altitude, and I have a line tool that can kind of make that happen, but yeah. Okay, let's fit it on here the right way. That's probably best as I'm going to be able to do it. Oh, not bad. Okay, so there's that last one there. There's the equilateral triangle. Hopefully I don't have to use the compass anymore because I'm going to ditch it. All right, there we go. That was number 17 through 20. Okay, construction. Spoke too soon. I got 4 more. We're going to do in-centers this time. Copy the triangle with the given angle measures, find the in-center, then construct the inscribed circle. So, I mean, this is something I guess you'd have to do like on binder paper. Literally, you'd have to use a protractor to copy those things down unless you're printing this thing out. And even if you are, these are very small pages to do this for. Okay, I'm okay with these ones being bigger. Not fully huge because I still got to make these. But basically, on these ones here, I have to draw angle bisectors this time. And with angle bisectors, again, only 2 are needed. But with angle bisectors, I need a compass. And I did say, I did not do this one during the whole lecture part earlier on. But I did say that I would show you how to do it if we have to. And here it is. So here's what you do. From a vertex, such as this one right here, you're going to kind of draw... Wait a second. Okay, from a vertex here, you're going to draw an arc and another arc that hits sides of your angle. So there's an arc right there. Oh, and this arc is hitting right at the bottom right there. So, okay, as long as it sides the angle. They need to be equidistant sides like that. And then what you have to do from each of those points where the arc intersects your angle, where the arc intersects your triangle side, the angle side that it went with, you have to just make sure that you can draw another arc here that this one can intersect with there. It does not have to be the same length as the initial arcs that you drew, just the ones that you draw that intersect need to be the same, like that. Now this is a line that you can draw from that vertex right there, and this will represent an angle bisector. This should be, boop, the angle bisector that's now dividing that 50-degree angle into 2 25-degree angles. So now this is congruent with that. That's what we just did. So we drew an in-center. Now, just make sure that it's large, that's far out enough that when you draw it, you know, just there's precision because you're going to use a straight edge to do that part, and that's how it's going to look. Okay, so there's one of them. We have to do this kind of 4 times, so. I didn't like that. Let's get that a little better. How about more like that? There we go. Okay, so there's one angle bisector. All right, let's do another one. Notice how I'm not doing it from the 90-degree angle. Okay, so on the second one here, I want to shrink this compass a lot more because I got to make sure that it stays within this side. It doesn't have to be this much. In fact, the first 2 ones that you draw, I'm just going to draw an arc right now like that. The first 2 that you do don't really have to be that far out. The last one is better to be, last one's better to be far out because you kind of want that away from your angle. Again, the farther out you are, the more precision that you'll have in general. You just want to make sure that it's somewhere in the direction of it'll intersect with this other guy. So that one, and then from this one right here, we got to draw another one. Just make sure it intersects. There we go. So that intersects right there for the 40-degree angle. Basically turn it into 2 20-degree angles. So from here, outward, boom. And there I have that one. So I can delete those arcs. I think that's probably close enough. Okay, I found 2. Whoa! I found 2 of the inscribed angles here, which finds my in-center. So my in-center is this guy right here. And once I find that point, I should really shrink this a little bit more. Once I find the in-center of this guy, then I could technically delete these other parts, which for you would be erasing these things here, or keep them, whatever. But we can now draw a circle that inscribes this triangle here. So inside of here, here's what you're going to do this time. Not go to the vertices, but go to any one of the sides. But you have to go perpendicularly to one of the sides. So this is where you would probably need to do a little bit more. Like I should do a little bit more here. You'd want to have a way of going perpendicular to it. I'm trying to think of how you would do that with a compass so fast. I guess you would have to... Okay, I know what you would have to do. I wonder if I should be doing that with you right now. Yeah? Okay, I'll show you this. Because I have the tool for it right here. Let's do it for this. Let's do it perpendicular to this one over here. Because I don't know what's exact this way, right? What's exact, I have no idea. It's close to that, but I have no idea. But you have to find that smallest point. That's the point, the closest distance. So here's what you do. You take your compass. This takes a while. And I don't know if the lecture portion would have told this because I skipped it. You take this compass and you draw an arc that's beyond it. You'd start with an arc that's beyond it, like this right here. It's not significantly beyond it, but it is beyond it. And then what you got to do... Oh my gosh. And then from there, what you got to do is find basically the perpendicular bisector from there, because these 2 points need to be equidistant from that point. This is kind of the converse of the perpendicular bisector theorem. 2 points that are equidistant at that point will mean that this point is on the perpendicular bisector of your segment. So from these 2 points is where you do that arc thing from before. You just draw 2 arcs somewhere and they have to intersect. They don't have to intersect there. Nothing. Here, let me go farther out. This arc needs to intersect with this arc in some way. Boom. Out there. And then you can draw a perpendicular bisector that goes through that. So there's a lot to be done. And this is just the first problem. And it goes through like that. And that kind of shows that that point should be on the perpendicular bisector. It wasn't perfect, but that's just because of the nature of the tools. So that's a rather close interpretation of what is the perpendicular bisector. What's the point of that being a perpendicular bisector? That's the short... I keep erasing the triangle. That's the shortest distance to that side from the in-center. Remember, it's not necessarily a midpoint. We're not looking for midpoints. That's the shortest distance to draw your in-center. Excuse me, to draw your inscribed circle from your in-center. So this should probably serve. Boom. Pretty close enough when all's said and done. What we're seeing there. You can see the tool's kind of messing up. But there we have it. My phone's going a little off the hook. Let me see what I got here. Not required to, whoops, look at. Okay, so there's number 21. I'm going to pause for 1 sec, though. I am going to take a look at this text. Okay, all taken care of there. We finished 21, yeah. All right, 22. Yeah, these problems, I mean, listen, for all intents and purposes, compass construction does take a while in general. But with this tool, trying to fit it on this screen so you can see it, and I keep deleting the compass, which is a problem. But I wish I could kind of shrink this figure and kind of manipulate it the right way. But it's hard to work with you guys on that thing. I don't know how many people are working this thing out. But if you are, hopefully it's making sense. I'm not teaching full construction, but I am doing the construction. So hopefully that works out. All right, so this is, it doesn't matter if it's acute or not, but it is. But it being acute... Whether or not it's acute, it will be, the in-center is always inside the triangle. All right, so let's see. I'm going to draw an arc here from the 55 like that, just outward. And from these 2 points, which are equidistant from there, you just got to draw 2 other arcs. I'm going to keep these kind of small this time. I don't want to go rambunctious. Just as long as it's far enough that I can intersect these 2 guys here. This guy and this guy here. Sorry if it's going to be less precise as a result. But I think I've overstayed my welcome on some of these. Now draw a line through there. See, I hate when that snaps differently once I get it there. Maybe this software someday will address itself on that. I'll be as precise as I can with that once I'm there. Okay, there's one of them. One of the angle bisectors. Let's go for another one. From the 85 right here. Let's do another couple arcs. Arc right there. Let's extend this one out so that here, and ooh, I might be going right on it. And then here, close. All right, so this from the vertex through there. Boom. All right, so where those two are meeting is the in center. Somehow that was a lot faster. I guess maybe just the way I went about doing this didn't change a lot of widths. Work that thing out. So that should be roughly the in center there. I'm going to go ahead and draw that. Now we're not done though, right? We still have to do the perpendicular bisector portion of this. So let's maybe go to the third side for that. And, you know, once again, I could draw it straight down literally, and my tool will kind of snap into what straight down is like. So it should be something like that. But let's go ahead and give that one a shot and do it the way that I mentioned here before, which is draw yourself an arc that can reach that other side twice. So here and here. And those 2 points are equidistant from here, which means that that point is on its perpendicular bisector. And we construct perpendicular bisectors from the compass as so. We have to just make sure that we draw 2 sets of arcs that will, yeah, sure, make it the exact same length. That'll overlap there. Oh, yeah, if you keep it on that same, I guess I could do that as well. If you keep it on that same path right there that it hits through that point up top, then you have one of the points that it actually hits through. Literally that one, and then another one. That makes sense. I could have totally done that to begin with. Now when that goes out, boom, like that, that means that that's your perpendicular bisector. That's as straight as I can make it as far as things go. That seems to make a lot of sense. So there's the perpendicular bisector. Now, all we need on the perpendicular bisector is just that point that it's hitting, so we can shrink this to that amount, right? That's the point. Shrink it to that amount, so then you can draw your circle. Ooh, that didn't really pan out. Let's maybe lower that a little bit so we can decrease the width. I can't really get that on a perfect swivel. Best I could do, y'all. So maybe it's not a perfect in center, right? Pretend like it is. Yours was probably more perfect. Again, mine doesn't snap well. I didn't extend mine farther out. You know the drill. All right, that is number 22. Okay, 2 more. Number 23. Doesn't matter that this is an obtuse triangle. This will still have an in-center inside of your triangle. It's not a circumcenter. Let's not delete the compass this time, please. Let's just move it out of the way for a second. Okay. Angle bisectors. I don't know if it's easier or harder to do the big one or small ones. Let's do the big one. Maybe more room for error when it comes to the arcs being farther away from each other. That arc and this arc right here. I guess they're not farther away. Well, yeah, they are. Okay, and then let's actually stretch this out this time a little bit. So boom, an arc there, and an arc, boom there. So where they intersect is where I want to get that drawn. This is way off. So the 135-degree angle has been broken up into 267.5-degree angles. Yes, that's what I was looking for. Okay, there's one. Let's do a second one. Let's do it off the 20. Actually, let's do it off the 25 just because the way that this thing's oriented. So let's do here, and then let's extend that out a lot more. All right, an arc here and an arc there. Yeah, see, I think when these things are closer, there's going to be a lot. Yeah, there's a lot more error that can, I guess, be had with that one, which is not as fun. That's why the obtuse one was a good one to do. Otherwise, this probably would have been way off. It's kind of intersecting right there, I guess. So there's my in-center. It's where those 2 other guys are intersecting. Let's get this one out of the way. So this one looks like the in-center. One more time, just revealing that in-center is inside of the triangle. Of course, it has to be. It's the one that inscribes the circle. Looks like this is a lot closer to here. I'll tell you what, these look a lot closer to here than it does to there. And actually, when you look at this angle right here, that does not look like it's really bisecting it. So I'm going to move this one over to what kind of, in an eyeball fashion, looks a little more accurate to a bisector, because clearly this had a lot of error when it came to me rotating that pivot. So, okay. That's all I'm going to do off that. Okay, so there is my in-center. Let's delete all the things that's not the triangle. Or the in-center. And then let's do some of that other perpendicular bisector stuff. I'll do it from arc. And, oh, that goes outside of there. Darn it. Let's shrink it. Okay, arc. And arc, yeah, because you have to hit sides of this other segment. Where do they intersect? You have to mark it off that. Now, again, if you do keep this length, this is a good idea. If you do keep this length, you just have to draw it on the other side, because technically it should hit that point again. So we're good on that. We don't need that point. We just need these two arcs to intersect together if you don't change the size of the compass. So this one, oh, it didn't hit. Let's see. This one and that one. Let's do that a little more. Man, this pivot really... When I pivot this thing around, apparently it's not going right where I had it the first time. So now when I draw it again, you can see where some of that error really shines. Yeah, that's not that far out. Let's draw it like there. That's the perpendicularness, but it's probably close enough. So what did I find there? The perpendicular, the shortest distance to that side, so that I can now fix my compass width to that length. Oh, I totally deleted it. Fix my compass width to that length. And try and draw its in-center. Let's go. Let's go. So rotate it. And resize it. See, I can't. It only snaps so well or not. That's really just the best I can do. I can't change it. I'll have to manually change the size. Yeah, only so much I'm limited with my software for sure, guys. All right, so that is number... That's the idea, right? That is number 23. Okay. All right, let's go to number 24, last one of this set. And I really hope there's no more compass construction after this. I legit do. This is a lot for... This is a lot. I already did one, stupidly for me, I did an example during the example set. That was not what I should have done. I should have realized, I thought they were showing you that, hey, see, it works, not, hey, you're going to have problems like that. That was my fault. Now, you have an equilateral triangle, which I'm trying to decide if there's anything here that can make this easier to discuss how you can save time doing something. One thing I'll mention is this. I don't know if that helps. Oh, the perpendicular bisector will also be at, well, duh, it will be at the midpoint. The angle bisectors will intersect at the midpoints. The angle bisectors and the perpendicular bisectors are the same line. Perfect. That's what I want to say. Angle bisectors and perpendicular bisectors are the same line. So after I draw an angle bisector, that will help, or the angle bisectors, that'll help because I already will then have the perpendicular, not the perpendicular bisectors, but the perpendicular line is also the perpendicular bisector. I know what I'm saying. I'm sorry if you don't. Basically, I'm going to have to do less work in the end, and I'll show you what I mean when I do that work. So I'm glad they gave me this problem. Less work for me. So this guy, when I draw this right here, not only is this an angle bisector dividing this into two 30-degree angles, if it were like drawn to scale and all that, into two 30-degree angles, this is also the altitude, that goes into there, right? Oh, here's another way of saying it. The in-center and the circumcenter are the same point. That's the best way of saying it. The in-center and the circumcenter are the same point. That then says that those perpendicular bisectors are also the shortest distance from the in-center to that point, all that kind of stuff. So basically, after I draw a second one of these and I find it, I'm good to go. I'll just kind of do the in-center after that. So let's do it off this one this time. Boom. And extend that guy out. But we are technically doing the in-center because we're drawing the angle bisectors. We're constructing them through angle bisector construction. So I didn't do perpendicular bisectors or anything like that. So here's the second guy. Now, if I did do this accurately, let's see how close we actually are to a proper in-center / circumcenter. Because the third guy, I can use this tool and make this go straight down. That's pretty close. So that looks to be pretty good. Not perfect, but that looks to be kind of within the ballpark of what we were trying to do. So this is a pretty proper in-center / circumcenter when I did that. That third one is just to kind of confirm that I'm near about the right spot. So let me get rid of that one. In fact, I'm going to get rid of all of them. Not all of them. I'm going to get rid of at least 2 of them. Because you know what? Let's save one, because this is also that perpendicular shortest distance. It is. Now, I'm not going to draw a circumscribed circle, only an inscribed one. But if I did draw a circumscribed circle, I use this same center, which is the cool part. So I saved myself time. I didn't have to do the perpendicular bisector part. Looks like I won't be able to snap to the perfect spot. Apologies. But when I draw, oh, that's not bad. When I draw around this right there, you can see the inscribed action. It's actually pretty good. All right. Wrong thing to shrink. Okay. I'm just happy that I'm done with those. Yeah, I'm not trying to be here forever either. All right, there are 21 to 24 doing those ones. Let's move forward. Number 25 and 26 are error analysis. Let's move to a fresh new page. Get rid of that compass forever, hopefully. Number 25. Describe and correct the error in identifying equal distances inside the triangle. They say GD is equal to GF. Well, here's GD, here's GF. Now, the problem is they're doing these. What this thing found was the in-center. You have bisected angles that are concurrent right here. That would be the in-center. But they continued those bisected angles lines through here and just assume that those are the ones that are equal length. That's not true. The ones that are equal length are the perpendicular distances that you would have here. When they say correct the error, this is what we'd have to do. We'd have to create new points and find those perpendicular distances and kind of say it's those things. These would all be the same length from that in-center. So not those angle bisector bits. So it's hard when they say correct the error, as in like do it right, because I don't have new points to do it off of. But let's just say that. The angle bisectors are concurrent at the in-center of the circle, which should create, here's me correcting it, which should create equidistant lengths perpendicularly to the sides of the triangle, not as an extension of the angle bisectors. Such as the work shown. So they just extended those angle bisectors and said like, oh, from the in-center to there, those are equal to, no. That's not how it works. So I can't really correct it because I can't really I'm saying how they should have done it. They have to get the perpendicular parts. Not perpendicular bisectors, just perpendicular shortest distances. And that's what it is. All right, number 26. TV equals TZ. It's probably a similar kind of thing. TV equals TZ. Yeah, no, because TX would have been it should have been equal as well. These are now perpendicular bisectors here, which makes this the circumcenter. Remember the circle that goes around here, which should make these things the same length right here. These are all the same distances. And I can point out what those distances are because those vertices are labeled. So I can actually correct this error here. So like the last one, they said in-center, this one's circumcenter. T is the circumcenter of the triangle. That's how you spell it. T is the circumcenter of the triangle. However, the perpendicular bisectors would not be equal in length, at least not in this case. Instead, TW should equal TU should equal TY. The distances from the circumcenter to the vertices would be the same. There's number 26. Great. All right, number 27. Modeling with mathematics. You and two friends plan to meet to walk your dogs together. You want the meeting place to be the same distance from each person's house. Explain how you can use the diagram to locate the meeting place. Okay. So I don't know where I guess from the doors, but oh, this kind of snaps. Let's see. I'll have to just wing it, just right in the middle of the houses. I can't even do that. Let's do this, and that. All right. So say that we have kind of a triangle that's mapping out the houses. This is like looking from Google Earth or whatever. From here, you would locate the meeting place by finding what do they want? The meeting place to be the same distance from each person's house. You'd want to find the circumcenter. So, and this would be kind of an obtuse triangle. So you'd want to find the circumcenter of here. It'd kind of be probably somewhere out here. I don't know where. But you want these distances to be the same. Boom, boom, boom. Like that. Those would be the same. And the circumcenter would be found by finding the perpendicular bisectors of this triangle and find their point of concurrency. Find their circumcenter. So that's how you would do it. So let's see. I'll try and kind of do one right here just through this craptastic stuff. So perpendicular bisector there, looks like a little closer. Perpendicular bisector there, and sure, perpendicular bisector there. Here's that circumcenter, which makes this, and this length the same. If you believe it, you shouldn't, because I didn't do good perpendicular bisectors. So that's what you would do. Your friends draw a triangle with your houses, with the houses as the vertices of the triangle, and find the circumcenter of that triangle. I don't know if I need to describe all the stuff, but perpendicular bisectors, where the perpendicular bisectors of each side of the triangle, or two of the three sides, are concurrent. This would be the same distance from each person's house. And it would be outside of that triangle if this is truly obtuse. So there's that. All right, number 28. You are placing a fountain in a triangular koi pond. It is a triangular koi pond. Look, they're koi fish. You want the fountain to be the same distance from each edge of the pond. So here's an edge of the pond, here's an edge of the pond, here's the sides of the triangle. Where should you place the fountain? Explain your reasoning. Use a sketch to support your answer. So this time I'll kind of copy and paste this one over as I use a sketch to support the answer. I guess they're telling you to sketch a different thing, but I have the actual koi pond itself because it is a triangular koi pond. That's so cool. This one is all about the edges of the pond, not the corners, not the vertices. They're not talking about that, but just any wall, basically. So what you're looking for is the in-center in this case. I want to draw an angle bisector on C. I'm not doing compass construction, but I want to do an angle bisector there on C, an angle bisector on A, and if all worked, that doesn't look like an angle bisector. And if all worked according to plan, an angle bisector on B, and then boom, you'd be meeting at some sort of in center, like that, whatever. And then that in center, the big in center, that in center right there, you'd want to find perpendicular, whatever. That's the in center. The perpendicular distances, this one, and this one would all be the same. Ideally, the same distance to any edge of the pond. If you had to swim, if the koi had to swim to a wall, they would swim the same amount to any direction from the in center. What are they putting there? A fountain? And that makes sense because maybe you want the fountain to go all the way to the wall of any edge of the wall, but not fly over. So actually, that's a good reason that you'd want to do something like that. So anyway, you'd want to find the in center of the triangular koi pond. Triangular koi pond by finding the angle bisectors of the triangle. Determine their point of concurrency. And determine their point of concurrency. and by determining their point of frequency. Sorry, I'm trying to get the English right. Because you don't have to do anything else from there. It's not about perpendicular bisectors. You found the incenter. That's what you'd want to find in that situation. Okay, number 29, critical thing, 29 to 32. Complete, always, sometimes, or never explain your reasoning. Now, what I've mentioned for always, sometimes, never things is always means always true, never means never true, or always false, and sometimes means sometimes true, sometimes false. Don't just assume that it's a sometimes. In fact, never guess if it's a sometimes. If it's a sometimes, that means because you know an example when it is true and an example when it's not. So it's not one of those like, oh, if you don't know, guess C kinds of things. No. All right, let's see what they say. The circumcenter of a scalene triangle is blank inside the triangle. Now, scalene does not describe whether something is acute, right, or obtuse. And if you don't know what a scalene triangle is, basically all sides are not, no side is congruent. So just any old triangle, like that's like here, boom, that's a scalene triangle because that side length's not the same as that or that. And this looks kind of obtuse. Well, that circumcenter would be on the outside of it if it was obtuse. If I had a scalene, kind of looks equilateral. If I had a scalene acute triangle, it would be inside. And if I had a scalene right triangle, it would be on it. So the circumcenter of a scalene triangle is sometimes inside the triangle. They say explain your reasoning. So let's type this then. So number 29 is sometimes. A scalene triangle can be obtuse, acute when it's inside, right when it's on it, or obtuse when it's outside. So sometimes it's inside when it's acute, sometimes it's not. And I think that's the best way. I should have just explained. I'm saying what a scalene triangle kind of can be, but just say when it can and when it can't in a sometimes situation. Sometimes it's harder to explain your true versus your false. If a perpendicular bisector of one side of a triangle intersects the opposite vertex, then the triangle is blank isosceles. I want to say sometimes. The only reason is because the exception would be an equilateral triangle. Is an isosceles triangle an equilateral triangle? I believe an isosceles triangle is only when exactly two sides. I'm literally going to Google this. Is an isosceles triangle... Is an equilateral triangle an isosceles triangle? Oh, when I started it, predictive text. Every equilateral triangle is isosceles. Oh, okay, good to know. Okay, always. So, I don't even know if I knew that. You know what? I knew that. I'm kind of an idiot. Yeah, always true. What are they saying? They're saying this. I want to describe it to you so you know why I'm answering this. Okay, isosceles triangle, such as this one right here. They're saying the perpendicular bisector of one side, if it intersects the opposite vertex, that's also the equivalent to saying drawing an altitude from this vertex through that side like that. And it also is the perpendicular bisector, all this stuff. I mean, this kind of explains the perpendicular bisector theorem. The whole idea of the perpendicular bisector creates two equidistant points, that kind of thing. So that's how I'm going to explain it. This explains that this is confirmed via the perpendicular bisector theorem. The only thing I was not sure about is, can we call an equilateral triangle isosceles? Of course you can. Sorry for thinking otherwise. What happened? There we go. Okay. Number 31. The perpendicular bisectors of a triangle intersect at a point that is blank equidistant from the midpoints of the sides of the triangle. Okay, so 31. So perpendicular bisectors, so they intersect at the circumcenter. The circumcenter is equidistant from the vertices of the triangle. What do they want? They said the midpoints of the sides of the triangle. No, it's not necessarily never true. It could be. I think we saw the equilateral triangle when that's true. But we'd look for that case to say from the vertices of the triangle. So this is a sometimes case, and that sometimes is very particular to only one exception. It is never true except in equilateral triangles. I think we saw that. If you saw me do the compass construction with the equilateral triangle thing and saw that the incenter was the same as the circumcenter and all that kind of stuff, then it would have equidistance. No other situation does that happen, but keep in mind a circumcenter is equidistant from the vertices, not the midpoints. Yeah. Okay, 32. the angle bisectors of a triangle intersect at a point that is blank equidistant from the sides of the triangle. Okay, so 32. The angle bisectors intersect at the incenter. The incenter is equidistant, yes, from the sides of the triangle. When they say when they talk about those distances from the sides, they're talking about the shortest distance, the perpendicular distance. That is what the incenter theorem is all about. That's what the incenter is all about. This is always true. This is the nature of an incenter. That's what incenters are. Okay, let's move forward. Number 33 and 34. Find the coordinates of the circumcenter of the triangle with the given vertices. So we did circumcenters before with these, right? So we're looking back at graphs. Honestly, I'd rather do graphs than compass construction, but if I had to pick and choose, you know, why can't I do neither? So, but maybe, just maybe, these are going to be a little more challenging, right? So these are all in the first quadrant. So A is at 2, 5. B is at 6, 6. And C is at 12, 3. The problem with C is it is outside of my window range here. I can just guess this again. 9, 10, 11, 12. All right, 12, 1, 2, 3 is C. Doing the best I can with that one. A is at 2, 5, and B is at 6, 6. Now, one immediate thing that I'm seeing right here, of course, is that the none of these are vertical or horizontal or whatever. So we're going to have to work at opposite reciprocal slopes. It's not the worst thing. We're going to have to work at opposite reciprocal slopes to make that happen. Now, we do have to do it. C has to be involved somehow. I can do the midpoint from A to B, but it wouldn't be pretty. In fact, the best midpoint I'd want to do is from A to C, because that will be an integer. The midpoint from A to C is between 2 and 12. That midpoint is 7. That's 5 away from 2 and 5 away from 12. And between 5 and 3 is 4. So this, let me connect these. I'm sorry. So okay. So one of the midpoints, I think I used red before, is 7, 4. That doesn't really look to scale much, which means C is probably off as a ordered pair itself, but kind of like that. We would have to do its opposite reciprocal slope. I'll get to that. Let's find another midpoint. Let's go from, let's do this one from A to B, because we can tell where it's supposed to be. It's at 2 away and then halfway up. It should be that guy right there. Okay, now we have to track this. I have to do a little bit of tracking on these things and kind of draw those lines. So this slope here is down 1 and over 5. So the opposite reciprocal is 5, like up 5 and over 1. So 1, 2, 3, 4, 5, and over 1 like that. Or down 1, 2, 3, 4, 5, and left of 1 like that. I don't know if I already mentioned this, but this is an obtuse triangle, so the circumcenter is outside of the circle. So I expect to extend really this other direction, but I want to extend these as much as possible before I get that started. So I want to make it look as accurate to the line as possible, because these really should be a drawn to scale thing. Outside of that C kind of being a mess, this should be pretty on point, unlike my compass construction things. Now this other one, here's the only problem, is this is in between 2 points, but this was up 1 over 4, so the slope should be -4. So instead I'm going to go down 4 and over 1. This kind of weird part is I'm going halfway in between points. So down 4 over 1. At least it's only halfway. I'll tell you what, though. I don't know if this lands right on an ordered pair. 1, 2, 3, 4. 1, 2, 3, 4 over 1. Like that. Unless I drew the third one to really confirm where it should go. But this otherwise should be intersecting right in an ordered pair, and this really doesn't. What do they want? Find the coordinates of the circumcenter of the triangle with the given vertices? I mean, if they want me to actually find it, I'm going to have to use it. I'm going to have to use algebraic means. Unless I messed something up there, I'm going to have to use algebraic means for that. So let me confirm that everything was good. Oh, wait. Yeah, opposite reciprocal. So down 1 over 5, up 1 over 4. Let's make sure all my points are right. Yeah, because that's not an integer ordered pair. So, the only way, if it's not an integer ordered pair, is through algebraic means 6, 6, 12, 3. I'm just making sure my points are right. 7, comma 4. I mean, those are proper midpoints. Slope, up 1 over 4, so it went down 1, 2, 3, 4 over 1, down 1, 2, 3, 4 over 1. Looks right. I mean, looks right. So, okay, I don't know that exact ordered pair. So here's what you would have to do in a case like this. You have to find the points of intersection for these through, I keep saying algebraic means. You need to find out the equations of these two lines. And then you have to set those, you have to find the x that makes those work and plug them in to find the y's. So that's what I have to do. So here's what I have. I have an equation here. I'm using point slope form. I'm going to make this as easy as I can. So this is, for this one, this midpoint, by the way, that midpoint is at 4, comma 5.5. So this will be y minus 5.5, y1 equals a slope of negative 4 equals negative 4 times x minus x1, 4. And then this equation has a slope of 5, and that point of intersection is 4, comma 7. So this is y minus 7 equals 5 times x minus 4. Oh, it's 7, comma 4, not 4, comma 7. 7, comma 4. So 4 here and 7 here. Okay. I'm going to copy and paste those down here so I know what I'm looking at. Y minus 5.5. I feel like I have something wrong beyond this, though. I don't know why they'd give you a graphing one to do this unless this is exactly what they want you to do with it, work this thing out, but it's not really well taught that way. Okay, I'm going to get y by itself in both equations. Like, I'm going to distribute negative 4 here, so y minus 5.5 equals negative 4x plus 16, or y equals negative 4x plus 21.5. Not a beautiful number there. And then, I mean, that's part of the point. This isn't going to be pretty. And so this one's going to be y minus 4 equals... I'm sure... Now, if there's something that I messed up with the equation of the lines, my bad, guys. Y equals 5x minus 21. Okay, so we have an equation here that says that y equals this, y equals that. We're going to set these two equal to each other. So, like these expressions here. So I'll have 5x minus 21 equals negative 4x plus 21.5. If I add 4x to both sides and if I add 21 to both sides, I get that. And I divide by 9. I had a calculator. I mean, 4.72 repeating. I don't know what I want to do with that information. Obviously, that would be a rounded thing if I do that. I'm just going to say 4.72. I mean, I don't know what they want me to do with that. There must be something. I'm just going to pause for a second. I want to make sure I didn't make a mistake, because otherwise I'm going to edit this out. Okay, just upon a quick review, I don't think I'm doing anything wrong per se. I'll say there's one minor mistake that I'm making right here, which this wasn't x minus 5, this was x minus 7. So I'm going to change this little guy here. So it's going to change some of the numbers at the bottom. So let me change that. But I don't think I'm doing anything wrong. Midpoints and stuff are good. So this should be a minus 7. So I copied something wrong. That's a problem. So that's going to be y minus 4 equals 5x minus 35. And then y equals 5x minus 31, not 21. So when I set those two things equal, we'll have 5x minus 31 equals negative 4x plus... That's still 21.5 in my eyes. I can't see how to change that. And 9x equals, I don't know, 52.5 right there. So I divide by 9. I still don't see anything great with what's going to happen when I divide by 9. I'm going to go for a fraction answer of some sort if I can. And I don't know how to... Let's see, x is 52.5 over 9. Let's expand that first. So like 105 over 18. And now let's reduce that back. Divided by 3, 35 over 6. So I'm going to work for that x answer there. Okay. The y value, let's plug in 35 over 6 into one of these. I'm going to use that one clearly. So y equals 5 times 35 over 6 minus 31. And I'll tell you how I caught attention to this thing. It's not that I noticed this was a 5. It's because I noticed that 4.72, that can't be 4.72. Oh, could this be 35 over 6? 35, yeah, 5 points. Yeah, that totally could be that. So I'm going to go off that. Anyway, so 5 times 35 is 175. 175 over 6 minus and 31 times 5 is 155 over 6. So that's going to be 20 over 6, which is 10 over 3. I don't know if I'm doing that right there. I might have made a little mistake in the math. So that ordered pair, the circumcenter, will be at 35 over 6, comma, 10 over 3. I don't see kind of a faster way for me to go about that. I'm going to make sure that my numbers kind of lined up correctly for that last one. Something sounds way wrong. That can't be 10 over 3. That's going to be something down below. Okay, I did something else wrong in my numbers there. Let's see that. 31, times 6, not times 5. Time out. Let me do that again. 31 times 6 is 186. So minus 186 over 6. Okay. That'll be negative 11 over 6. Okay. Sorry about my math, guys. This is a solution guide video. If your teacher assigned it to you, it's going to be kind of mean anyway. That's the answer I'm going with. It's the answer I'm going with. This thing is not intersecting at any great points. And yeah, I don't know why they give it to you other than unless they expect you to use all that stuff. And I did not use slope-intercept form. I did use point-slope form. So sorry, I'm not going to work hard to get a y-intercept of something that might be far off when I don't need to. So one of them was kind of off. All right, number 34. Let's see if this one goes any better here. I'm going to bring in a graph, and we get, this is the third quadrant. So D is at negative 9, negative 5. E is at negative 5, negative 9. And F is at negative 2, negative 2. There's some symmetry here. So much so that I wonder how I can pick out that symmetry. This might be isosceles. Negative 2, negative 2 is here. That's F. D is negative 9, negative 5. And E is negative 5, negative 9. All right. Yeah, it must be isosceles, right? Yeah. Does that help me? It's isosceles. It's acute. Does that help me with what I want to do? I don't know, maybe. With one of them being, I think I want to work off this midpoint right here. So I'm going to use this one and say this is, down 4 over 4. So here's a midpoint at that guy. And I get to rise and run, up 1 over 1 like this. So I know that this thing, and this will run right into F. It's isosceles. So one of those perpendicular bisectors goes into the vertex. So I know there's that guy. So that's pretty cool. So that does help. There's one of the perpendicular bisectors, and I know it's going to intersect inside the triangle, so I don't really have to extend it any farther than that. So we just got to choose one of these other ones to make this happen with. Let's just do this one over here. So the midpoint of negative 9 and negative 2, it's halfway in between. Average those, it's negative 5.5. So here, and then between negative 5 and negative 2 is negative 3.5. Negative 3.5. So this guy. So from here, that slope was up 1, 2, 3 over 1, 2, 3, 4, 5, 6, 7. So the opposite reciprocal is down 7 over 3. 1, 2, 3, 4, 5, 6, 7, and right 1, 2, 3. So we'll see if this precision lands me right there. I'm sure hoping it does. And up, these were at half points. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3. So it's actually outside of this. And then up 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, in where my F is over there. So this is right there. I'm going to just assume that this is my circumcenter. That looks pretty good to me. I don't know about you guys, but I'm going to say, am I allowed to do that? Gee willikers, I don't know if I'm allowed to do that. Because those were decimal points, so I don't know if I'm hitting that at all. Especially if I'm going down 7. There's no way that it's going to be hitting that for sure. All right, I can't know that for sure. One equation is going to be pretty nice, though. If I keep extending this out, this is literally just the equation y equals x. So on one of them, I have the equation y equals x. Very beautiful. The other one, not so pretty. I have those decimal things. I will write point slope form. That's y minus, my y1 is negative 3.5, so plus 3.5. Y plus 3.5 equals, and then I had negative 7/3, I think was my slope. Negative 7/3 times x. So I gotta write this as fractions. I can't write 3.5. I'm gonna write 7/2. Negative 7/3 in x plus 11/2. This is the 5.5, the negative 5.5 thing. All right, let's work that one out. Y. Well, listen, y equals x. Could I just substitute x into here and solve? Yeah. So let's just have x replace it. X plus 7/2 equals, I don't have to go any deeper than that. Distribute the negative 7/3, so negative 7/3 x minus 77/6. There's no way this is an integer. Let's multiply everything by 6. Get rid of the fractions for now. So 6x plus, and this becomes 3 times, 6 over 2 is 3 times 7 is 21. So I'm doing times 6, and times 6. 6 equals, and negative 6 over 3 is 2 times negative 7 is negative 14. So negative 14x, and then minus 77. That'll look a lot easier. Add 14x to both sides, you get 20x. Subtract 22 from both sides, you get negative 98. At least it'll be kind of cleaner. Not perfect. That's negative what? Negative 4.9? Negative 4.9. If x is negative 4.9, so is y. And that, I mean, it makes sense that it's on a thing. So it's not negative 5, negative 5. So it's a good thing I did this. So y is negative 4.9 as well. So therefore, we have an ordered pair of negative 4.9, comma negative 4.9. So, okay, the writers of the book must have done these with intent, these problems here. And you have to do a lot more algebraically to solve them. It did say critical thinking, but I assume their critical thing was just there's no vertical and horizontal lines. Man, you got to do more in opposite reciprocal slopes. So they had never really had an in-between of problems where nothing was vertical and horizontal, but nothing was clean. That's too bad. All right, in exercises 35 and 36, find the value of x that makes n the in-center of the triangle. Let's see where they're going with that guy there. All right, for n to be the in-center of the triangle, your in-center is talking about angle bisectors going here, which means that these distances would all be the same. Now, this is, okay, this is one that's nice that you can, do some work on it. So what you look at here, I'm going to actually bring this over. Let me get rid of my little piece of art. Let's bring this diagram over. Let's do some work on it. Let's talk about it. That 2x that you see there should also be a 2x anywhere else you go on the blue. So, because these are all the same. So if that's 2x, so is nk, also 2x. And what you see now is a right triangle. I see a right triangle, right. Let's do a different color. I see a right triangle, right. Here, that's probably not even the best color either. What, green? See a right triangle right here. Okay, so there's that right triangle, and in a right triangle, and I'm trying to think of any other way I would do this, but my eye goes toward Pythagorean theorem. You have the length of both legs and the hypotenuse, and that's kind of a way to find a missing length of something. So I have 2x. So this is a squared plus b squared equals c squared. 2x squared plus 35 squared equals 37 squared. Now 2x quantity squared is also 4x squared. It's kind of solving using quadratics there. I know this number is 1225. I don't know what 37 squared is. Let's see. 37 times 37. 1369. 1369. Subtract 1225 over. I'm going to let the calculator do it. I don't want to make any mistakes. 144. Okay. 144. Divide by 4. I think that's 36. And take the square root of both sides. You'll get 6. Now, you could say plus or minus 6, but distances has to be positive. So x equals 6 in that case. That's what they said, right? Find the value of x? Yes. Okay. That is number 35. Number 36... What problem do I have to go to? 51. Okay. Number 36. I guess we copy this one over as well. It might be another Pythagorean theorem question. Yeah. And, you know, I'm not going to save time on this, but I can tell you what the answer is right now. 14x right here. Okay, so with this one, I guess the other one was a special Pythagorean triple. I wasn't actually aware. Or was it? I think so. This one's also a Pythagorean triple here. I will set it up with the Pythagorean theorem. I have a right triangle right here. 14x squared plus 24 squared equals 25 squared. The answer, I think, is going to be 0.5, 1/2 or 0.5. That's what I believe. So right here, 14x squared is 196 x squared, 24 squared is 576, and 25 squared is 625. 6x squared equals 49. Now, I know when I divide that, I'll get 1/4. Take the square root of that, you will get 1/2. So there's my x. We say, Mr. Robinson, how'd you get that? I know that this is a Pythagorean triple of 7, 24, 25. You'll probably learn that later in IM2 about special Pythagorean triples. I did not know that. I did not know the other one with the 35 and 37, though. I forgot what the other number was suddenly. All right. Oh, we got to do a proof. Proof. Where is the circumcenter located in any right triangle? Oh, write a coordinate proof of this result. Where is the circumcenter located in any right triangle? So a coordinate proof, I wonder if I can actually use a coordinate thing. I feel like I can't. I just have to do blank axes for this. Okay. Now, can I use it at the origin? I feel like I should be able to, and it should be nice enough that I do that because the distances will still be what they are. Okay, so I'm going to do this. I'm going to make, because it is a right triangle, I'm going to make the right angle at the origin like that, and I'm going to draw a right triangle as such. I'm going to make up some ordered pairs here. So here is my right triangle, and this is at 0, comma b, and this is at a, comma 0, and this would be at 0, comma 0. Okay? So in an instance there, am I allowed to just do that? It says any right triangle. I can't do it at the origin then. My bad. But okay, I'll just shift everything. But I can't call it 0, comma whatever. I have to kind of do some work off of this. So, all right, I'll move it off of there. So I have to change the order pairs. Okay, so let's call it. Let's call the. Come on. Let's call this order pair x, comma y. So if this is x, y, we're going to add a amounts to x here, where that's still y. And we're going to add b amounts to y like that there. Okay, now on the right triangle, keep in mind it's all about perpendicular bisectors of things, and it's really easiest to... Wait, it says where is it located? Is that all they asked? Oh, perfect. We just need the midpoint of these two right here. I don't need to do all the other stuff. But if you recall, the midpoint of this, midpoint of that perpendicular bisectors, they meet at the other one on there, which is the midpoint of the third one. So all I have to do is find the midpoint of this guy right here. The midpoint of that and that. Now they say I'd write a coordinate proof of this result. Oh. A coordinate proof doesn't... Oh, okay. So here's what I'm going to do. Let's find this midpoint and let's show that the equations of these ones represent the midpoint of that. I don't know if that is relevant. I think I just got to do a midpoint. I'm not sure, but this is what I'm going to do. Sorry. I'm not perfect on coordinate proofs here. So I need to find the midpoint of the x's. Here's an x, and here's the other x. You got to average those. And then I have this y, the y plus b. And then I add the other y to it, and I divide that by 2. And then that will be 2x plus a all over 2, and then 2y plus b all over 2. That's one version you could write. If I do divide them by 2, though, then I have a version that says x plus a over 2, so just do half of that a, and then y plus b over 2, so just do half of the b outward, and then that would be the location of it. Now, this location would be x plus a over 2 comma y, and this would be x comma y plus b over 2. In the same way, you just find the midpoints of those, and then this is the equation y equals y plus b over 2, and this is x equals x plus a over 2. So I don't really know if that's anything that kind of shows proofs within that, but yeah. If there's any other thing that they'd want to indicate, it's that all these points are the same distance away from each other, but I don't think there's a proof within there that we're talking about. It's just all about that being the midpoint. I don't know. I might be answering that one incorrectly. I'm sorry. But as far as this goes, if x and y are the points of your right triangle, your right angle, then and a and b are the distances out of the right triangle like that, you can do it like that. Oh, where is it located? It's located on the right. It's located on hypotenuse of the right triangle. Okay, here's where I think that I'm kind of messing up this proof. And I'm sorry, I am going to move forward. But here's where I think I'm kind of messing up on this proof. We got to prove that it's on the hypotenuse. I'm just doing the hypotenuse thing there. I don't really know if that works out a proof in that way. I mean, this other one would do that same thing. I would just be drawing it in that direction, vertical and horizontal lines, and it shows it's there. But here's the other problem. This isn't any right triangle. They didn't say the right triangle has to have vertical and horizontal distances. That's the other part that I kind of lose myself. I can't say I know this answer in a great way. Sorry. That's the way I'm going to go about this problem. Didn't ever say I was perfect on these. I don't know if you were given that one. Number 38. Number 38, proving a theorem. Write a proof of the in-center theorem. Okay. That's a lot. They want to keep me here for a while. Okay. Given... That's a lot of givens. I mean, that's all I'm saying. And the final proof statement, I really want to work the maze direction of this as far as like really think backwards as far as what I need to get to and how I need to get to there before even caring about the givens themselves. The angle bisectors intersect at D, which is equidistant from segments AB, BC, and CA. Wow. That is a lot, and look at these givens. All right, as far as saving writing, I'm going to at least do this. Sorry, but I'm going to save myself some time there. Okay, now that's a lot of givens. Remember, not every single one of these is going to work out the way that we wanted to there. So given. Okay, that's one. Given the triangle... And given that this segment bisects that angle, and that segment bisects that angle, and those three are perpendicular. We only have two bisectors. AD bisects that, BD bisects that. Do we have... Oh, we don't have CD. The angle bisectors intersect at D, which is equidistant from there. Okay, I'm looking at triangles. I don't know if I see congruent triangles to work out this proof. I guess the next... I think they're hinting... at having us draw this third angle bisector. Maybe if we do that, we can work something out. I actually want to pause and think about this one. Give me a second. Okay, I thought about it for about 8 seconds. And I'm going to actually... I don't think they do want you to draw CD. What I'm actually thinking is this. They only draw 2 of them. Because... And I haven't thought about the proof, but... Clearly, when you have those congruent things, you probably have some sets of triangles that are congruent. And what I was thinking was, and I lost them now. What I was thinking, if you have congruent triangles, right, whenever you do a bisector like that one, I'm going to be able to do congruent triangles, for example, like here and there. That should work out. or congruent triangles there and there. But the question is, how do I get to the proof? Because those are congruent triangles. I mean, that works out. But the angle bisectors intersect at D, which is equidistant from all three of those. Where's CA? Oh, equidistant from there. Okay. Oh, that might not be that much then. That might not be that much. I just got to lay it out still. They intersect at D. Okay, so I have to do a couple triangle congruence proofs, though. I think that's the big thing. So bear with me on that, all right? So let's start by looking at these two triangles here. Let's prove them congruent. In order to do that, we have the bisectors. Okay, BD bisects angle CBA. So that means that we can say that angle FBD is congruent to angle EBD. That is definition of angle bisector. You know what? We can probably do the same two things at once. We'll say that one is true, that those are congruent right there. And we'll do the same thing over here. GAD congruent to EAD. I'm surprised they even have it marked. They state it's bisected, but it's up to us to state that those are actually congruent. So that's number 2. I'm doing both at the same time. Number 3, let's look at this one first with those right angles. Well, with all the right angles, if they're all perpendicular, that means that angle BFD, I'm basically going to state they're all right angles. Angle BFD, angle BED, angle technically AED, we need to mention that one, and angle AGD are right angles. This is definition of perpendicular lines. 4, these are congruent to each other, but there are specific ones we need to be congruent. We need to be angle BFD congruent to angle BED, angle BFD congruent to angle BED, and then the other set is angle AED congruent to angle AGD. It's based on the triangles I'm looking at. Congruent to angle AGD. That's definition of right angles. All right angles are congruent. Okay? And so here's what we have. We have 2 sets of angles that are congruent in all those triangles that we're talking about. I should mark this one as a right angle as a result of that. Now we're going to say reflexive property, that this segment's congruent to itself and this segment's congruent to itself. So, 5th one, 5. How do I want to say this? 5 BD congruent to itself by the reflexive property, and then AD congruent to itself by the reflexive property. I hope it's okay that I'm doing these all as kind of like I'm mixing and matching there. And now those 2 sets of triangles are congruent in their own separate way. Those sets are congruent in their own separate way. And there's something else I see that's kind of interesting I want to make mention of in a second. But 6 triangle BFD, that this top one right here, I'm going to say this triangle is congruent to this one, and then I'm going to say this triangle is congruent to that one. So BFD is congruent to BED, those would correspond. And then triangle AGD is congruent to triangle AED. These are both by angle side. Doesn't matter that they're right triangles, just the angle side, like that. Now here's the cool part. By CPCTC, we can say that this segment here is congruent to this segment, and that this segment here is congruent to that segment. But here's the really cool part about this. There's a shared, that's the same segment in both of those, that ED. So I'm going to say FD is congruent to ED, and GD is congruent to ED. They're both congruent to ED by CPCTC. And notice that also means FG must be congruent to GD as well by extension. That's why I get to mark them all the same. FD congruent to GD. They're all congruent to each other by transitive property of congruence. Transitive property of congruence. This should be enough. Let me see if there's anything else I need to state before my proving statement. I can't write. I'm sorry. Let's see what my proving statement is. Oh, it's over here. The angle bisectors intersect at D, which is equidistant. Okay, well, clearly they intersect at D. There's nothing I can say with that, except for the CD. I wonder if there's something I got to state on that. I might have to go further. Let me really think about that here. If I say draw CD, is that enough to say it's a bisector? Well, those points are equidistant from there. There's probably more I have to do. But now that I noted that all those... Okay, this is going to extend... Okay, this is going to be kind of weird because I'm going to lose some of this this line right here. I hope you're okay with that. I just got to keep extending this thing down. Okay, I have all that down. Now let's go to 9... where I'm going to say draw CD. It's just a construction thing. By construction. That did not guarantee that it was an angle bisector, though. How do I want to say that? Here's what I'm trying to say. There's the angle bisector theorem, which states that that a point on the angle bisector is equidistant to the two sides of an angle, which is true because these 2 points are the same distance away. I'm just trying to decide, okay, here, I'm going to say it like this. I'm going to say FD is congruent to GD, therefore the length of FD equals the length of GD. That is the definition of congruent segments. So that means there's equidistance, which means D is equidistant. 10. D is equidistant from G and F, which is the definition of equidistance. A lot of definitions. I don't remember ever doing this many definitions with proofs. I think because I'm generally doing CPCTC and stuff like that. That's the definition of equidistance when you have the same equal distance away. So 11. So if that's equidistant, so if D is equidistant from those 2 points, then it's on the bisector. That's the converse of it. So draw. Do I say draw an angle bisector? Excuse me. D. I don't know how to say this statement. I want to say that D is on C's angle bisector. So I'm just going to say this. Draw angle bisector for angle GCF, which passes through D. That's kind of a weird statement. Generally, I wouldn't make a statement like that. But this is all about the converse. Well, for one, it's a construction by the converse of the angle bisector theorem. So what we're doing there is we're showing that because D is equidistant from G and F, then it is on the angle bisector. So when we draw the angle bisector, we know it will pass through D. That's the big thing that we're doing on that one there. That's my belief on how I want to say that. It's kind of weird, but that's what I'm going to do. So I'm going to draw that, and then now we know that the angle bisectors intersect at D. That's the last part we had to figure out. and it's equidistant. We already know the equidistant part. That's already there, which is equidistant from AB, BC, and CA. I don't know how I want to reason this because it's two different statements. The angle bisectors intersect at D, which is equidistant from AB, BC, and CA. Okay. I think we already kind of noted the equidistant part. Definition of equidistance, I think, is already there. How do I reason with the second part, though? Maybe that's the angle bisector theorem thing right there. The reasoning is it's constructed. I don't know. How about this? I'll say converse of angle bisector theorem thing here, and I'll say via construction. This, unfortunately, that is a weak ending for that part of it. My construction shows the angle bisector was there. It's maybe this statement 11 is statement 12. You know what I mean? At least the the angle bisectors intersect their part, because we just saw that this one goes through there. So maybe those are kind of the same one. And I already did the definition of equidistance up above. So that's kind of, that's my proof. That's what I'm working off of there. It's kind of tough. They're really challenging me with these ones here. I don't know how they expect a student to do that. You know what I mean? I'm talking about this stuff, and I've lived this, man. This is my life. I haven't done geometry in a long time, but still, this is something that I should be able to reason with. All right, number 39. Explain the difference between the circumcenter and the incenter of a triangle. Fair enough. So this should be a quick one. The circumcenter is the center of a circle. Now, remember, you don't have to draw a circle in these things, but is the center of how about a proverbial circle? Of a proverbial circle that would circumscribe the triangle at its vertices. I mean, that's what circumscribe it means. It would intersect at its vertices. Whereas the incenter is the center of a proverbial circle that would inscribe the triangle at its sides. And the implication that, of course, is it's at the closest distances there. That's what the inscribe part talks about. That's one portion of it. There are other things we could say. So that's one thing I'm going to say. That's the end result of what you get. How do you obtain it? The circumcenter is the point of concurrence of the perpendicular bisectors of the triangle, and can be found in, on, or outside of the triangle. Inside, on, or outside of the triangle. The incenter is the point of concurrence of the angle bisectors of the triangle, and is always inside the triangle. Now, the last statement I'm going to make is really the first one again, which is talking about the equidistance. The circumcenter, I guess this is not very quick because I'm describing any way that I can describe it. The circumcenter is equidistant from the vertices of the triangle. Hence the circle part. And the incenter is equidistant from the sides of the triangle. Okay. So that really is the top one again, that circle thing. That was probably the better way to put it, but the way of seeing it with the circle, I think, explains that for you guys a little more. All right, number 40. Is the incenter of a triangle ever located outside the triangle? Explain your reasoning. I've said that a lot of times already. It's not. No. No, because angle bisectors are always inside the triangle. I think that's good enough. If they intersect at angle bisectors, then that's where they're going to be. And they intersect at the angle bisectors. And the intersector, the incenter is the point of concurrence of said angle bisectors. So, no. Okay, that was a lot faster. All right, let's keep moving forward. Still 11 more problems. Number 41, modeling with mathematics. You are installing a circular pool in the triangular courtyard shown. It is a triangular courtyard. You want to have the largest pool possible on the site without extending into the walkway. Copy the triangle, sure, and show how to install the pool. Let's do this, 41. Copy the triangle and show how to install the pool so that it just touches each edge. Then explain how you can be sure you could not fit a larger pool on the site. So it's a circular pool. Show how to install it so it just touches each edge. Explain how you can be sure it could not fit a larger pool. Okay. Well, this is all about in-center stuff, right? So show how. I'm going to do the angle bisector thing. I'm not going to get deep into angle bisectors, but just let's actually use a line tool this time. Let's go angle bisector concept. You do an angle bisector here for this one. Remember, it bisects the angle. It doesn't bisect the side. You do an angle bisector here, best as you can. And then, I don't know, let's try the third one and see if that looks like that would be close. I'm not looking at my in-center. I'm just looking at the idea of angle bisector. Wow, that's not even close. Oh, I'm sorry, the green is what I have to go with there. Okay, let's do that angle bisector. That would be, maybe there. Okay, that's looking a little bit better. Not perfect. This one should be more, oh man. I don't know if I can do angle bisectors by eye at all. It would probably be closer to like that. Yeah, let's say it's kind of closer to that-ish. Okay, so maybe like that's my in-center, right? So, okay, so there's an in-center with that thing here, and then the pool, you know, perpendicular distances are probably, you know, like those guys, like right there. And then you build a circle around that thing, like wee, whatever. And then there's the pool around that in-center like that. So, explain, so just touches you. So, okay, so that's just my idea of it. I'm not literally going to do a construction thing. I refuse. But explain how you can be sure you cannot fit a larger pool because a circle has a radius, which means equal length in all directions. These perpendicular, quote unquote, perpendicular distances to the sides are the shortest distances, well, are the longest possible distances, or radii, that the circle can go without extending beyond the triangle. Okay. That's part A. Part B, you want to have the largest pool possible while leaving at least 1 foot of space around the pool. Would the center of the pool be in the same position as in part A? Justify your answer. I mean, I'm 1 foot. I mean, the question is that should I just go 1 foot in from there? At least, you know, is the 1 foot in from there the best place for that space? I think so. Now, as long as that's the answer, then yes, because we're going inward perpendicularly, which means we're still maintaining our radii space. So as far as that goes, I'd say yes. I believe I'm having the concept right that just going inward from there would still maintain the best pool thing. So yes, because going inward from the, are they calling the walls? From the edges is still working directly inward toward the center. Since those lengths are perpendicular. Really, since they're perpendicular. I don't know if I'm saying that right, but yes. Yes is my thought. Yeah, this is, man, this video, man, I'm not doing too hot on this one. Number 42, modeling with mathematics. Archaeologists find 3 stones. They believe the stones were once part of a circle of stones with a community fire pit at its center. A circle of stones. Okay. They mark the locations of stones A, B, and C on a graph where distances are measured in feet. Explain how archaeologists can use a sketch to estimate the center of the circle of stones. Let me, problem's kind of cool. Because they have, like legend says. I kind of like that. For A. And B, copy the diagram I just did and find the approximate coordinates of the point at which the archaeologist should look for the fire pit. Okay, so it looks like B is my second thing I'm going to do. Basically, what are we saying? So with the circle thing, that means that something would circumscribe this, so we'd be looking for the circumcenter. So for part A, find the circumcenter. How archaeologists can use a sketch. They can find the circumcenter. They can make a triangle, construct a triangle, ABC, and find its circumcenter. We know how to find a circumcenter, or at least we should. So part B is going to be doing that. So B, here we go. So we copied it down. Let's do that. Now this is where we might have to do construction. Or ruler basis, or half a distance. Oh, no, you know what? This is a graph. We can just do this. So we construct this. Bam, bam, bam. And then let's do midpoint things. Hopefully this one is not... Oh, these might not be very good. Okay. What's the best midpoint I can find? From 210 to 13.6. 10 to 6 isn't terrible. From 1 to 6 is 6 to 3. Okay, I don't like that one. And 2 to 6, 10 to 1. Okay, I'm going to do it from A to B and A to C. At least I'll have one midpoint that's on something right. So from 10 to 6 is 8. And then from 2 to 13, half the distance. Halfway from 2 to 13 is 7.5. So this guy right here is 7.5, comma 8. This one from 2 to 6 is 4. So 4, comma, and it looks like it's going to be 5.5. From 1 to 10, half that distance is, yes, 5.5. So 4, comma 5.5. I believe this is the second question for which we have a 4, comma 5.5 on that. Now, we do need to locate, they said approximate, didn't they? Find the approximate coordinates. Let's see if it's near a near an integer set, and then we can call that the approximation. How does that sound? So I'm going to use like a light green when I draw this. Now this slope is down 9 and over 4. So if I go up 4 and over 9, then I can, so 1, 2, 3, 4. And over 9 from 4 is 13. So I'm going to go all the way to here. Boom. I'm going to draw that perpendicular bisector like that. It's kind of that light green there. I don't know if it's going to go at near any great integers. Let's go, archaeologists. Because keep in mind, guys, the whole circle thing, I'll draw the circle after, but the circle thing, this was a circle of other stones, right? So that is why we're doing circumcenter. This from A to B is down 4 and over 11. So half of that, no, excuse me, not half of that. So the opposite reciprocal is like up 11 over 4 or down 11 left 4. Now, I don't know if I can do that really well. Let's just go down 5.5 and over 2. That's half of those. 1, 2, 3, 4, 5.5 and over 1, 2. That's kind of the best approximation I can get with that because I can't count down 11 while I'm doing that. So I'm just going to draw it like that right there. Okay, so the circumcenter looks to be around this area right here. It's not perfect by any means as in near integers, but it does look like the x value is very close to 7. It's probably not perfect, but it's close-esque to 7, 7. I'm just going to go ahead and say that. It's about at 7, 7. Definitely not perfect from there, but the drawing may be perfect. So with the drawing, let's try and expand this thing outward from here and see that we got what we were looking for when we drew the circle. I'm going to draw it to one of the vertices here and see what we got. Yeah, that looks pretty close to a good circumcenter. I mean, clearly there's something that was maybe just off just a tick, but that's a pretty good circumcenter right there. Looks like we got the idea. It's around 7, 7. I'm going to go with that. All right. Number 43. Let's get my little circle. Point P is inside triangle ABC. Is it? No. Point P is inside triangle ABC and is equidistant from points A and B. On which of the following segments must P be located? Okay. Point. Let me just draw, and I'm just going to rough out what they're talking about. So, okay, here's ABC. Point P is on ABC and is equidistant from points A and B. That doesn't mean it's equidistant from C. For all we know, point P can be on C. So I'm going to make up, it's right here. So, okay. On which of the following segments must P be located? On segment AB? No, that's not necessarily true. You can see what I'm doing right here. It can be over there. The perpendicular bisector of AB? I believe that. Yep. That's the perpendicular bisector definition. On segment AC? No. The perpendicular bisector segment AC? No, not necessarily true. Oh, this might not be multiple choice. This might be multiple choice, not multiple selection. Perpendicular bisector of AC would mean it would be the circumcenter. This doesn't have to be the circumcenter. So it doesn't have to be concurrent with another perpendicular bisector. So B as an answer. I'm now realizing it's multiple choice and not multiple selection. Number 44. Critical thinking. A high school is being built for the 4 towns shown on the map. Shady Hills. Each town agrees that the school should be an equal distance from each of the 4 towns. Is there a single point where they could agree to build the school? If so, find it. If not, explain why not. Justify your answer with a diagram. Well, I'm trying to think, because we've been talking about triangles. So I'm trying to think if there is a center. This isn't a square. I mean, there must be still. Can you do circumcenters for... Okay, I'm going to say no. Here's what I'm going to say. Here's what I'm... It says justify with a diagram. So here's what I'm going to talk about. And I'm going to use this diagram, but I don't know if this is going to work. You can do 2 sets of triangles. If the circumcenters for those 2 triangles are the same, then okay. But if they're not, then no. So let's say I have this orange triangle here. And then let's say I have this, I need another color that'll stand out, this light blue triangle right here. In order for any of these triangles to have a single point that would be equidistant from those points would be equidistant, would be its circumcenter. And that's the only point that would be equidistant from those points. So we'd have to make sure that the other point also does that with any of the other 2 points of the triangle. Now, I'm not saying this doesn't have it. So listen, I'm not saying it's impossible. I'm saying what you'd have to do is find the circumcenter of both of these. It's not one that's inside of there or something. So is there a point where they could agree to build a school? They say if so, find it. That depends on whether this thing works or not. It's only possible if they have the same circumcenter. That's what I'm saying. So let's do this. Let's rough it out and see what we kind of get. I'm going to at least do the perpendicular bisector for this one between Lake City and Willow Valley. So like really, literally, I'm going to rough this out. I'm not using compass construction. So I'm going to like perpendicular. I'm really bad at doing this. And in the middle, sure, kind of like that. And let's do like the perpendicular bisector of like this guy here. I mean, this one's going to be inside the triangle. Well, listen. I'm going to say no for this particular diagram. This is going to be have one that's inside the triangle, and this one's going to have one that's outside the triangle. So for this particular thing, absolutely not. Because the blue, that light blue one, would have a circumcenter that's like right there. The orangish looking one would have a circumcenter that's like right there. So for this diagram, no. In fact, the only kind of diagram that I believe would work would be any rectangle. A square is also a rectangle. I don't think it can work for any other shape. So it would only be possible if any two constructed triangles share the same circumcenter, which this diagram apparently does not show. Only a rectangle. This is my hypothesis. Parallelogram might work. No, rectangle. Only a rectangle. I don't know why I thought that. Only a rectangle or a square or a rhombus. No, only a rectangle or a square would be able to have such a system, such a feature, such a circumcenter. Okay, there's 44. Number 45. Making an argument. Your friend says that the circumcenter of an equilateral triangle is also the incenter of the triangle. Is your friend correct? Explain your reasoning. Yes, we had a question that had that, and that's what I mentioned. Your friend is correct. This operates under the perpendicular bisector theorem. I'm just going to say that because when you draw a perpendicular bisector in an equilateral triangle, the point of that vertex is on a point that is equidistant from the other two sides of it. Therefore, it kind of works, and that works for all three sides. For all three sides of the triangle. For all three sides of the triangle. It kind of just works out. We saw it. It worked. I don't know if my explanation's perfect, but we did a problem with it, and it just worked out. All right, 46. How do you see it? The arms of the windmill are the angle bisectors of the red triangle. What point of concurrency is the point that connects the three arms? The circumcenter. I don't know if they want me to say anything else on that. I thought they meant what it's called in the windmill. I'm like, I don't know. So the windmill. Oh, angle bisectors. I'm sorry. I was assuming they meant the windmill was all three equal side lengths. They didn't say that. They said angle bisector. So the incenter. Okay, so angle bisectors, incenter. I don't know how windmill has anything to do with that. So, okay, the incenter is the point of concurrency. It might be the circumcenter as well. I'd assume a windmill has equal arm lengths. The incenter is the point of concurrency. I should have typed this. Of the wind that connects the three arms. Should have typed this. But the incenter. Okay. Oh my gosh. I should have typed this. Even if I have a typo typing, which I have a lot, that would have been a lot faster. All right, number 47. Abstract reasoning. You are asked to draw a triangle and all its perpendicular bisectors and angle bisectors. For which type of triangle would you need the fewest segments? What is the minimum number of segments you would need explained? All right, so I mentioned it's the equilateral triangle. So the equilateral triangle, because number one, its incenter and circumcenter are the same, which means you only need two. So therefore, well, sorry, it's not because one, because its incenter and circumcenter are the same. Therefore, you only need to make two segments maximum. And that's exactly what I did on a previous problem. Right, that's part A. Part B. For which type of triangle would you need the most segments? What is the maximum number of segments you would need to explain? What type of triangle? Either, and if you understand the, well, a scalene triangle. A scalene triangle would. But I'm wondering if like an obtuse would or something like that. Triangle would need the most. And 4 segments would be needed. No. You'd also have to, wait, what do you want? Just the, oh, the perpendicular. Let me think about the first one again. I thought they said you just need to draw the incenter and circumcenter. You need to draw all the perpendicular bisectors and all the angle bisectors. What's the minimum number of segments you'd need? You would need 3 segments. The segments are the things. So therefore, you would only need to make 3 segments maximum. So let me say that again. 3 segments maximum. Because those are the segments that are made for the things. The incenters and the circumcenters are the same. So all 3 of them, basically. So, and I guess you need 6 segments here. I'm just wondering, the angle bisectors, what else do you want? You were asked to draw in all its perpendicular segments, the angle bisectors. You need 6. And all 6 segments would be needed. Scaling triangle would need the most because that would guarantee the that would guarantee the incenter and circumcenter are different. So would an isosceles triangle, I think, and all 6 segments would be needed. I don't know if I'm really saying that right. That's it. I don't know what they're asking there, because they're just asking to draw the bisectors. They're not asking to draw the incenters and circumcenters. So, I don't know. It's kind of off. Give me 1 second here. I'm going to pause this. Okay. All right. Number 48. Thought-provoking. The diagram shows an official hockey rink used by the National Hockey League, NHL. Create a triangle using hockey players as vertices in which the center circle is inscribed in the triangle. Okay, so this center circle here. The center dot should be the incenter of your triangle. Sketch a drawing of the locations of your hockey players, then label the actual lengths of the sides and the angle measures in your triangle. These are tough for me to do with the technology that I have at hand. I have to say that. I have to admit, this is not an easy question to answer with what I have. It's not an easy question for you as well, because you can't copy down the diagram in the same way. So, and you don't want to draw proportionally to scale and stuff. It's really hard to play with this. I kind of am like under an oath that I'm going to do every problem, because who knows what you're going to be assigned, but I'm not assigning this to my students. So, now I'm not, now that I see the problem. I'm going to kind of like sharpen, like enhance these a little bit. All right. That's a 30-foot diameter circle right there. Yes, indeed. I'm going to lock this in place. I'm going to lock those in place. Okay. The diagram shows an official hockey to create a triangle using hockey players as vertices in which the center circle is inscribed. Okay, so listen, there's not much it's very, you can be very open-ended with this thing. This just needs to inscribe it, which means if you have a point, like look, I'm going to make a hockey player, okay? I'll put it on that dot right there. Okay, there's a hockey player A. I just need to draw tangent lines through this. Whoops. I need to draw tangent lines through this guy right here, across this way, and this way. There. Okay? Now, on one of these lines, on either of these lines, I can place a hockey player somewhere else, such as right here. I can call him B, and I need to draw a tangent line to this, through this part of the circle, and wherever it intersects would end up keeping that circle inscribing this triangle. So like that. Tangent line means it only touches the circle at just that one point, the one that's the closest distance or whatever. So there's my hockey player C. So that is at least a drawing of a triangle with my 3 hockey players. That, at the very least, is something that I'm able to construct. Now, distances? I don't know. Let's see. Did they ask for something? Create a triangle with hockey players as vertices, in which the center circle is inscribed in the triangle. The center dot should be the in-center. Sketch a drawing of the locations of the hockey players. Then label the actual lengths of the sides and the angle measures in your triangle. I have a protractor. See, here's the problem with my lengths. Oh, okay. So we can do a proportion thing. That's fine. Okay, so I'll try this the best I can. I'm gonna like resize this so in some way to make this actually operate in a way that makes sense. So I'm gonna make 30 feet. Let's shrink 3 centimeters to 30 feet and see if we can kind of work off that. Okay. Or shoot, this is gonna be pretty small if I do that. Let's make 1 centimeter 30 feet. I'll grow it back again. Let's make 1 inch 30 feet. This is the problem, all this resizing stuff. I gotta figure this thing out. Yeah, you're just watching me play with this thing. I should probably pause this until I figure this thing out. Because I gotta keep shrinking from the top and then put it in there. As long as, because this is just a proportion deal from here, because who cares what the size is? It's just relative to what you do. The answer, I mean, the answer's not the same for everybody. The answer's different depending on what you built. So you built something here. So for me, I'm going to say 1 inch is 30 feet. 1 inch equals 30 feet. We'll do proportions based on that. So I can do measures. I'm going to do the side length measures first, as long as I don't change this size. And now this is, the only problem is it's now so small, I can't tell what I'm looking at anymore. So from B to C, this is 1. I'm going to say 1 11/16 of an inch. So 1 11/16 inches. I'll equate that in a bit, but that's segment length BC. And then some of these, a lot of these are going to kind of probably be close to the same length, because this is almost, not equilateral, but kind of, it's not very scalene. It's not like obtuse. This next one here, really, this is a lot easier on paper. This is really hard for me to see what I'm measuring. I'm sure you can tell. This next one here is like 1 and, this is pretty close. It's 1 10/16, so 1 5/8. So AB is 1 5/8 of an inch. Again, we're going to do the proportions in a bit. And then the last one from A to C, I probably should have done one a little more extreme. Why are the hockey players all in these equilateral triangle? So that means if they're close to equilateral, then these degrees are also close to like 60 degrees, right? Which is kind of neat. And then this one, this is a little farther out. This is 1 15/16. I think they go by 16ths. So AC is 1 15/16. Now, first of all, first thing I'm going to do is translate these into like improper fractions. So 27/16 of an inch, 13/8 of an inch, and then 31/16 of an inch. So with those in mind, you know, I get to multiply those things by the 30 feet basically. So which 30 times that, 27/16 equals something. I'm going to go to the calculator for that. And then 30 times 13/8. And then 30 times 31/16. And then we'll just kind of get approximations of those ones. So that will be 30 times 27/16, 50.625. 50.625 feet. Okay, that's not an approximation. None of these actually will be actual approximations. 30 times 13/8, 48.75. I could use something called the law of cosines to get these angle measures, but that's pre-calc or calculus or whatever. 30 times 31/16. I'm not going to do that. 58.125 feet. 58.125 feet. So that's what those measurements are there for those lengths. Okay, now they say find the angle measures of these. This is where I'd use a protractor, and I'll see if I can actually make this thing work out in any way that's feasible. I'd really have to shrink this thing, though. I don't know how to resize it. There we go. I can't even see these angle measures from here, so let's see. Let's do a rotation of this guy. Where's the edge? So if the edge is there, all right, I think I'm on it. So now I can move this guy. Oh, there it is. I can move this guy over to this. Okay, I can actually mark these things here. So if I forget how I hit it, like that. Did it create an angle for me? Oh, that's a 72 degrees. So I got a 72 degree angle for B. This is 72 degrees, like that. Once I find the two angles, the third one is like, 180 minus the sum of those two. So I'm just going to find a second one now. So a second one. Let's find C here. So this second one is going to be about 36? No, 50. What is that? 126. Oh, I must be reading it wrong. So 126, so 54 degrees. I don't know what I'm reading with that other thing then. Was the other one 72 then? So 54 degrees for angle C. These are, of course, approximations, but 54 degrees. So A, 72 plus 54 is 126. So this also must be 54-ish degrees. I mean, they're pretty close to each other because those are pretty close lengths, 50 and 48. Those are as close as can get. It's kind of close to an isosceles triangle, so I'm just going to go with that. So that's number 48. That was really not a good question. Oh, the 200. I could have used the 200. I totally didn't see the other lengths. I just used 30. My bad. I could have used other ones. Okay. Last three questions here. In exercises 49 and 50, state whether you would use perpendicular bisectors or angle bisectors. Then solve the problem. All right, so 49. And thankfully, when I said that I would save enough room in my computer for 3 hours, thankfully I did that because now I'm nearing running out of room, actually. I didn't delete enough things yet, so I got to get these ones done. You need to cut the largest circle possible from an isosceles triangle made of paper whose sides are 8 inches, 12 inches, and 12 inches. Find the radius of the circle. Oh, they're actually making me use paper. I refuse. I'm going to pause and make something here just to save recording time and see what I can do. Okay, so I made one. I did the best that I could with the isosceles triangle tool, and I measured it to 12 and 12, and I got the 8 from this other one. So I'm going to move this out of the way. So our goal is to make an in-center and then find out what that length is. So I'm going to save time from you guys. I'm going to kind of just rough it. So I'm going to use like because at least I can snap this first one down, right? This one can go straight down like that, and then that can be my angle bisector for this first one, which is also the perpendicular bisector on the other side, which is good because I can use that point also for this thing. That's a good thing for this problem. The other ones are going to be kind of rougher. I'm going to work my best on getting the angle bisector on this one as like, sure. So I'm attacking it that way, and let's see if that kind of worked out. Because if I can get a circle out of that, great. Otherwise, it's compass construction, and not a fan for the time being. This is a pretty asinine take on what it is that I got to do. So it looks like it's not quite there. Let's move it down a little bit. Let's try this again. Closer, a little bit more. See, I get the luxury of being able to just undo and check this again, and a little too far. And this one should be good enough about right there. Okay, so from here, if that's my in-center, I can draw a circle that's going to go out like that. Okay, that's pretty good. And knowing that, well, I don't need the perpendicular bisector thing anymore. I just know it's going to hit out there. Okay, so now the question is, how long is that? So I'm going to keep this ruler thing the same length. And the 12, this is in centimeters. I know it says inches, but I'm just going to measure in the same way. Whatever number this is what I'm going for. I got to go, I'm going to go this way. I got to go straight up and down. That's how I can use this. And it's going to measure pretty close to 3. It's a little under 3 inches. So a little under 3 inches, about 3 inches there. So that's what I'm going for, radius of the circle, about 3 inches. All right. So number 50. On a map of a camp, you need to create a circular walking path that connects the pool at these ordered pairs. Here's the problem. I can't go that far, but I can go by 2s, maybe. Pretend like I'm going by 2s instead of 1s. At 10:20, the nature center at 16:2, the tennis court at 2:4. Find the coordinates of the center of the circle and the radius of the circle. Okay, I'm going to actually grow this, not shrink it. Okay, so I'm going to go by 2s. So this is going to be a 20 now, and this is 10. Okay, so at 10, 20, I'm going to have this guy. This is the what? Connects the pool. The nature center at 16, 2. And the tennis court at 2:4. So tennis court, okay? Let's do that. Okay, what do they want? You need to create a circular walking path that connects them. Find the coordinates of the center of the circle and the radius of the circle. So the coordinates of the center, we got to find the circumcenter. For this guy here, we'll go by midpoints. I think this one will be a decent midpoint here. 1, 2, 3, 4, 5, 6, 7, 8. Half of that is 4, and over here. So this is at the point, these go by 2s. So this is 6, 12. These other ones, probably not great in comparison. Well, this goes from 2 to 16. Actually, this might be okay. So remember, they go by 2s. So it goes from 2 to 16, and then this goes to 3. So I think this is halfway between 2 to 16 is 9. It's not going to look good, but it goes halfway in that way. So this is 9, 3. Just because the scaling, it's going to be unfortunate. Otherwise, it would have worked pretty well. Anyway, so this one, what? Up 4 over 2. So up 2 over 1. So down 1 over 2 like that. And down 1 over 2 like that. So this would work out for this line here. We're finding perpendicular bisectors. Remember that? So here's a perpendicular bisector of this one. And then this one is perpendicular bisector. We're doing a down 1 over 1, 2, 3, 4, 5, 6, 7. So now we got to rise 7 and run 1. 1, 2, 3, 4, 5, 6, 7, and run 1 like that. I'm just going to go ahead and plot that the best I can. And you can do this on your graph things as well that are drawn. So, okay, I'm just going to imagine. I'm going to imagine that this is the circumcenter. Remember, it's got to be equidistant to these 3 lengths here. So I'm going to imagine that that is actual an integer set of values. Maybe it is, maybe it's not, but that is 10, 10. Looking pretty good. Now, it does say find the radius of the circle. That means I need to find the distance to any of these. The nice thing is I can go straight up. 2, 4, 6, 8, 10. I believe my radius is 10. I'm going to go with that. I don't know if those were exact or not, but it looks pretty good. I might not have to use any distance formula stuff. Kind of like it. Leaves me with one more problem. Number 51, critical thinking though. Point D is the in-center. Let's see, 51. This is not a proof. Point D is the in-center of triangle ABC. Write an expression for the length of x in terms of the 3 side lengths AB, AC, and BC. Okay. Let's see if I can think about what they're asking. It's the in-center. All right, so we have angle bisectors here. So the angle bisect... Well, x is the same... Okay, x is the same on all 3 of these. Each of these would be an x. Okay, that's the first thing. X, x, x. Now, with that in mind... AB I was going to use Pythagorean theorem, but they said AB, BC, and AC. They're talking about the side lengths, not the middle parts there. I'm pausing and think about it because I'm running out of recording space. Okay, so here's the best answer I can think about for now. I was thinking Pythagorean theorem. Maybe there's something there. I can't think about it. I'm thinking more in terms of area. Because x represents the heights of these different triangles in here. Let's imagine that I'm talking about this triangle that's like this guy. So I got a triangle right there. AC is the base and x is the height, right? And then I have another triangle, and I have just 3 different triangles. So this one here, x is the height of that one, and then x is also the height of this one, because height is always perpendicular to your base. Now, if I add those 3 areas up, that equals the area of the entire triangle. What's nice about that is they all use AB, AC, and BC in some sort of way. So here's what I'm going to say. Imagine this first triangle I talked about, right? That area would be 1/2 base times height. And then plus, let's look at this triangle here. That's 1/2 base times height. And then the last one here is 1/2 base times height. Now, when you add those together, that equals the area of the whole thing, 1/2. And I can call this the base and this the height because they're perpendicular. AC times AB. All right, squeeze it right in. Now I can double all these. I just realized that. So you can double all these here. So the fractions are gone. So I'll have AC times X plus AB times X plus BC times X equals AC times AB. I'm going to reorganize these alphabetically. I can factor an X out of all 3 of these. It's a common factor. Let's do it kind of alphabetically. AB plus AC plus BC. And let's call this AB times AC. And now I can solve for X by dividing both sides by AB plus AC plus BC. So X will equal AB times AC over AB plus AC plus BC, like that. That's the answer I'm going with. I can't really think of anything else there. That should work in terms of an answer. I don't know if that's the answer they'd want or if there's a better simplified way that I can do that. Which actually gets more to, was my radius correct when I did that 12, 12, and 8? Let's see. What was my 3 inches, my 3-inch radius? I'm going to try this. 12, 12, and 8, right? Which ones were the 12 and the 8, though? Which is the BC and the AC and all that? Does that matter? AB, AC, AB, BC? It does matter. AB and AC would be these guys. Oh, no, that wouldn't work there because this is a right triangle and that's not one. I couldn't use that for that. Okay, I'm going to leave it there. Okay, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Or I apologize for you having watching this one. This was not a good video. This section had a lot of technological faults with me. It had me questioning my own beliefs on how I'd go about doing something with it. So I apologize for some of the things I had to do with you guys here, but you entered my domain, and I hope you can trust me for other problems that we have to do. It all depends on how much they explore the geometry. These are hard questions, and they're different questions, and they test you quite a bit. They test me quite a bit. I gotta go. Thank you so much, guys. Take care. I will see you in the next one.